going back has put Miami on the map in this area and, you know, opened up a huge arena of research. So thank you for coming.
Is this pointer active? Because I have a film group on one of the slides and okay. So you know, I think it's will have some lights. I mean, this is all the language. Yeah, do you want to say? So we'll talk about African dust transport to the Caribbean Basin and the southern United States, also the northern. No, in South America is also impacted as well, but I'm not going to say much about that. So the arrows do okay. So these are the major questions we want to address or points we're going to make, and that is that we're impacted by dust from Africa. Africa is the largest global dust source, about half of the global total. There's a, how do I get the pointer here? But, no, that's okay. That's okay. But where's the pointer? Oh, to the bottom.
It doesn't seem to work very well. I can help you.
Pardon?
It doesn't seem to work very well. I can
I'm just trying to find the pointers.
point.
Oh, this, okay. Okay, good. Thank you. So, Africa is responsible for about half of the global total. Back there. Okay. Not responding. Okay. Oh, really weak. Okay. The major dust sources are located in this region, and this is in fact the global dust belt that affects a large part of the world. The lower plot is shows the aerosol optical depth, dust aerosol optical depth across the globe, and the point of the circle is that Africa is impacting much of the North Atlantic region and the Caribbean Basin. So it has a huge impact. So I want to talk about how this dust transport to the Western Atlantic impacts the air quality, the Caribbean Basin, and the Southern United States. And the African particles are detected routinely in standard air monitoring equipment, PM 2.5, PM 10. I'll show some of that data. And it's present in concentrations that can affect air quality and human health. And it's interesting that Chris Holmes mentioned that the EPA is considering reducing the 24-hour standard from 35 micrograms per meter to 8 to 11, I think you said. In that case, we're going to find that the entire region, the Caribbean Basin, in the summer months is probably going to exceed that standard almost all summer long at all sites. So we have to have a better understanding of what is driving this transport and its impact on humans in the region, and also plays an important role in climate processes. It itself is a product of climate variability, meteorological climatability, but it's radiatively and cloud activists. So radiative forcing agent is a cloud cloud nucleus, and therefore can feedback on the climate itself. So I'm having such a problem with this. There we go. Okay. So this is a this is an image of a huge dust event, the Godzilla dust event in June 2020, and this is the largest dust event in the past 50 years. I say 50 years because it's our data in Barbados that sets the standard And I'm going to use it as an example of the regional transport. But even though it's anomalous in concentration, it's still representative of the way this stuff is transported across the Atlantic and to the southern US. So this is a two models, and now I got to activate that. No, I don't even see the button to activate the video. We're going to pass over that.
I
because he's doing-
can, which video?
The one on the left. Oh, there you go. Fine. So this is a model, the GEOS model of the event, forecast model, and you can see how the dust enters into the Caribbean and over the Gulf of Mexico, gets caught in the westerlies, and it's actually transported out across the east coast to the North Atlantic. And if you do the other, different, the one on the right, different model, but it's always basically the same thing. It doesn't run for as long so you don't see it. Huge event, huge event. So when you look at the air quality measurements throughout the southern United States, these are the PM 2.5 measurements based on standard network sites. This is a paper by you et al. 2021. And these are the two major 2 days, 26 to 26 and June 27. And the PM 2.5 data is color coded here. But under the new standard that is being proposed, essentially all these sites would be exceeding the 24-hour standard. So it's huge, huge impact across the region. This is what an African dust event looks like. Aircraft photograph. You have very dense haze and you have very suppressed clouds. And this is due to the fact that the dust is largely transported in an elevated layer, the Saharan dust layer, and you have strong heating of the desert surface over Africa. You get very deep vertical mixing. This shows it here up to 6 kilometers, can be higher. And this is injected out over the Atlantic. And it's very hot, very dry. It's long inversion at the base, which suppresses convection in the marine boundary layer. You can also get dust injected directly into the marine boundary layer. And about 5 days later, it reaches the Caribbean. The top is sunk to 4 kilometers, roughly variable. And during this process, you have these little suppressed clouds which are eroding the base of the layer. And that's the way a lot of the dust reaches the marine boundary layer. So it makes it difficult to model and also to study the dust transport phenomenon. So I'm going to show you data from a few sites. Here's Miami up here. Here's Barbados here. This is our site at Ragged Point, Barbados, a 15-meter tower. And we had a recent paper discussing the history of the discovery of dust in the Western Hemisphere. If you're interested, this is me in 1967, more hair, but this in the early days there's no electricity, so we sampled the dust by mounting nylon monofilament meshes in the wind and let the trade wind blow through it. We collect huge amounts of dust, even on relatively low dust days. And this is one of these meshes folded over, and that red-brown color is very characteristic of Saharan dust. You take that, rinse it out, and you have mud in your bottom of your bucket. And at our laboratory, we have hundreds of vials with African dust in our collection. This shows the results of some of our work in Barbados. The bottom part, the blue, is the monthly mean dust concentration at Barbados. It starts in late 1965, and you see a very strong seasonal cycle with a summer maximum. But across the record, you can see tremendous variability with time from year to year. And these are linked to climate processes in Africa. In the early 1970s, there was a sharp increase related to the onset of drought in North Africa. And even more dramatically in the mid-1980s, very intense drought that led to widespread starvation of humans and the livestock, and things ameliorate. And some of these big peaks can be related to things like El Nino, this one here and the one in 1997, clearly associated in some way with El Nino events. At the top, there is the annual up on the left axis, the annual mean dust concentration measured at Barbados. And on the red line is the Sahel precipitation anomaly plotted on the left or the right scale. It's plotted inversely. There's minus 25 up there and then the positive values here. So at the peak in the mid 1980s, there was a very intense drought, which is manifested in that Sahel precipitation record. So there is a link to climate, and there are other factors involved, of course, wind, and these are all linked together in some ways. It's a complex issue, which is difficult to deal with. Models have a problem with it. So this is what a dust sample might look like. This is from a station we had in Cayenne, French Guiana. And if you look at these slides, you can see, of course, mineral particles. Note that most of the particles are below or several micrometers diameter. You can see the scale, size scale here. But it's interesting that you often see biological materials. These are freshwater diatoms, and the dry lake beds are a very good source of dust. And in Africa, there were, during the Holocene, 6,000, 8,000 years ago, there were a lot of lakes which no longer exist. Notable among them was the Bodeli Depression in northern Chad, which has huge concentrations of freshwater diatoms. And you can see them when they're a dust storm coming out of Chad. You can see this incredible white plume traveling to the west, but it's still not clear to what extent that impacts on the larger scale dust transport. But so now I'll say a few words about the properties of the dust, the composition. These are science distribution measurements made during a field program several years ago. They were interested in measuring the isotopic properties of African dust. This was carried out at our station in Braggart Point, Barbados. And so you see here, the black dots are measurements by various instruments, PSI instruments, of course. And I can't bump this on. Anyhow, so you can see there we go. So you can see these black dots are the measurements by the SFPS, SEM, and APS. And the red lines are measurements with SEM, and the blue line are measurements of the East Atlantic. And you can see in transporting the dust across the Atlantic that you're losing the upper size distribution. And in fact, all of that dust mass is actually below 10 micrometers diameter. So measurements of PM10 are going to give you a measure of the total, in effect, measure the total African dust concentration in the sample. So now I'm going to show you some data from some standard PM samplers. These are geomes on Martinique in the Eastern Caribbean. And you can see the map where Martinique is. And there are 5 stations shown here. And early in the year, there's no African dust. So this is, local sources, things of that nature. Here's the first big dust episode that comes through in the spring. Spring dust episodes are sporadic, and then it goes quiet for a while. And then the summer transport begins, and this continues all summer long. And this only goes to June, but you would see it all summer long. And I point out that if you look at the PM10 concentrations, and also PM2.5, you will see that this exceeds, since PM2.5 is about half of the total of the PM10, you see that this exceeds people in these islands would be exposed to concentrations above the proposed new standard 8 to 11 micrograms per cubic meter of air. So it's continuous all summer long, this exposure. So there's really a question of what health effects are of dust, but normally that concern focuses on sporadic events, but I have not seen anything that deals with chronic exposure to mineral dust particles of this nature. In fact, it's very difficult to parse out the effects of dust on human health. because there have been really very few studies that focus in a very specific manner on mechanisms and the effects. So a few more slides to finish up. This shows the homogeneity of the dust size-wise. This is a ratio of PM 2.5 to PM 10 measured in stations during the passage of the Godzilla event. And these are islands. This is Martinique, station in the coast of Mexico, Houston, and Florida. And when the dust comes through, you have a very constant ratio of PM 2.5 to 10. And you can see this in the daily data, 5 years of data from Martinique, where the dust events all cluster essentially between around 0.3 to 0.4 micro the ratio is 0.3 to 0.4. So I'm just about finished. So now this is a record of the passage of the Godzilla event through the region, and you can see the station. These are all numbered. This is KN, the various islands. This is Guadeloupe. This is Houston, this is Florida, and it's PM 10, PM 2.5. You can use the numbers to gauge progress, but you can clearly see the advance of the dust front as it goes through the region, eventually exiting over Florida and Georgia to the Atlantic coast. A few words about the composition. This is the composition of Barbados and Miami dust, and it's shown as the ratio of the concentration normalized to upper crust abundance. And you see the complete spectrum of the range of elements here. And you see that Miami and Barbados track one another pretty well throughout the entire element spectrum. But some of these elements are very highly enriched, and some of the usual characters, vanadium, copper, zinc, things of that sort. Cadmium, I don't understand. But the point is that there are some interesting anomalies, but that in general, the composition at Barbados and Miami are pretty much the same. And again, this is tracking concentrations, and this is compares the concentration at Miami with Barbados. And note that the scales are different. This is 40 micrograms per cubic meter, about 70. So Barbados roughly has half the concentration that is measured in Barbados, and the peaks are lower, and also the dust season is shorter. And these are plots showing ratios of iron to dust and various elemental ratios. And again, for example, the iron to manganese ratio just follows right on top of average crustal abundances. But when you get to things such as vanadium, you see different anomalies or differences, which are attributed to vanadium's common pollutant element from combustion of fuels. And these are a series of slides seeking to pick out the signature, in this case, the isotopic signature of African dust. The idea is that if you exceed the EPA standard, you can claim an impact of a natural phenomenon. So how can you identify African dust? And this is a series of studies that we did with people at the Texas A&M Shankar Shalom, and looking at various ways to get at the problem. And here you see the strontium isotope ratios against epsilon neodymium. And I won't go through the whole chart, but the African dust is all clustered depending on where the samples were taken in a distinct pattern that's very different from the catalyst Houston soils, things of that nature. And this is the same sort of information with epsilon hafnium against epsilon neodymium. So finally, I think that there's a real natural sources of pollutants, and you can think of the dust and the increased dust as possibly a pollutant due to climate change is driven by anthropogenic factors. So dust, this natural dust that we see can be, in a sense, anthropogenic. But we have a very poor understanding of what that impact is on human health, because there have been very few studies that have tried to assess that. Usually they are carried out in looking at a lot of studies in Spain, for example, where they often get African dust and they use epidemiologists to tease out how much of that of the physical impacts, the health impacts can be attributed to dust as contrasted to other pollutants, but that can be a difficult thing to untangle. A lot of concern about the role with asthma, and again, I just published a paper showing that African dust has no impact on asthma at Barbados, but there are other papers which manage to come up with various impacts. But a major issue today is that the models have very difficult time dealing with dust emissions and transport. There was a recent study that 16, this is the Zhao et al. Paper. Pointer is almost invisible. The Zhao et al. Paper, which uses the CMIP6 meteorological model, and they use 16 different groups that use various soil, dust, emission, and transport schemes. And the models, across those models, there was a difference of about a factor of 5 between the global emission rates for African dust. So it's still a huge problem. The major problem is that we really don't know what the major sources are and how they respond to changes in weather and climate, and specifically, rainfall, wind, and geological factors. And that remains an opportunity for people like us to track these changes over time, to see how the emissions and transport across the Atlantic vary, and whether this can be related to any driving factors. And with that, I end, but I show you a slide showing the region and various island and coastal locations in Africa that are engaged in aerosol research, and that offers the opportunity to coordinate these studies to get a sort of end-to-end description of these outbreaks and how they change with transport and time. It takes about 5 days to cross the Atlantic to the Eastern Caribbean, but the dust sources many are interior to Africa. Some are 7 to 8 hours, that's days away, 8,000 kilometers. The Bodolite Depression, for example, is 8,000 kilometers distant from Barbados and Cayenne. So I leave you with that challenge. Thank you.
Thank you, Jay. So for this next portion, we'll have the 3 speakers sitting in the chairs up here, and Shai Lee will moderate us. So yeah, you could just stay up there.
Because Aquila needs to leave because of teaching, so I will take over from here. So terrific presentations this morning. Thank you to give a brief overview of what about the air quality issue in Florida. So I think we are ready to take questions. So how about, okay. So how about let's start with questions for Dr. Chris Holmes.
So I had a question, and maybe this is my amazing here. I had heard in NPR talking about some of the controversy of some of the TMs and how well they're capturing some of the sugarcane burning events. And I noticed when you had your slide up and you were showing the region where the burning was occurring, there's really only one air quality monitoring site. Can you comment on that and how that might have sort of made people maybe not as worried about the issue as maybe should be?
So the Clean Air Act sets out statutory requirements for where air quality monitors have to be placed. And the requirements are that they need to be, that any urban area larger than about 50,000 people needs to have an air quality monitor. And as your population increases, you have to have more air quality monitors. So there's no statutory requirement to have a monitor in the sugarcane growing region. So that's a statutory reason why we don't have more. I think it's clear that our monitoring network in Florida is inadequate to capture the scales of smoke plumes. And it's not just in the sugarcane growing region. Most of these smoke plumes are on the scale of a couple of kilometers, and we have on the order of 40 sites across the state. And those are located in urban areas. And so the rural areas of the state are not monitored much at all. And so I think, for the rural areas of the state across the board, and other states as well, there's a lot of smoke impacts that are kind of missed by the current monitoring network.
Okay, I also have a question. I will use my advantage. So with climate change, will there tend to be more sugarcane growth, or there's supposed to be less? I'm very curious about this, how it will interfere with the wildfire and how
Yeah, so the projections suggest that, well, first off, there's a lot of uncertainty about rainfall projections in the southeastern US in climate models, in terms of whether it will increase or decrease. But the warmer projected temperatures lead to a higher risk of wildfires in future climate. However, I think our work has shown that with extensive prescribed fires, you can mitigate those wildfire risk. So I think you can potentially see a mitigation measure being to expand the use of prescribed fire to mitigate wildfire risk. And I think we're sort of near that point in the southeast US and very far from that point in the western US.
Okay, thank you.
So a quick question. Could the prescribed burn be used to completely eliminate the wildfire? I think you alluded to it, but I'm talking of completely eliminate. The second question is, what are the health impacts of prescribed burns? Is there any negative consequence?
Okay, so prescribed fires do not necessarily totally eliminate the risk of wildfire. But even if they don't prevent the wildfires, they're still helpful because the wildfires will be much easier to control if there are lower fuel loads on the ground. So that's an important reason for doing them, even if you're not outright preventing wildfires. To your second question, well, we know that PM from all sources impacts health. So yes, of course, there are going to be adverse health effects from prescribed fires. In my approach to this, however, is that my group will probably not be quantifying those adverse health effects until we have a more established method for quantifying their benefits in terms of mitigating wildfire risk. Because a distinction that I like to draw is that prescribed fires in wildland settings have a public benefit of mitigating wildfire risk and risk to the community. And so you have to offset that benefit against the health and air quality impacts. Agricultural fires don't have that public benefit. They're primarily for the purpose of reducing costs for a landowner.
Yeah, follow up on that actually related twofold questions. One is with the prescribed fires, is there currently, given that you mentioned, for example, that one needs to get a permit to carry on with prescribed fire, is there a protocol in place where the permitting processes coordinated with atmospheric conditions. But when you noted in one of your last slides, New Orleans or Alabama as having one of the worst areas, is there a correlation when these prescribed events are scheduled, that atmospheric conditions are looked at beyond a local region to a larger scale region, and therefore a toolkit or guideline is somewhat, then produced to advise? And the second question is, in context of air quality, what's ongoing work as far as indoor air quality, and what is the built environment system response integrated, when we're discussing these health impacts?
Those are great questions. I think Florida is really a leader in accounting for meteorological factors in the permitting process. With that said, there's a lot more that I think could be done. So just what they do currently is if the National Weather Service issues a red flag warning, meaning there's a risk of wildfires, then no permits will be issued. They also have a very quick system that allows anybody who calls in to request a permit, they can use a latitude longitude point on a map, and it will very quickly sketch out where a plume is likely to go. If that plume is likely to impact a road, a hospital, a school, a larger urban area, no permit will be issued. But that is really focused on visibility hazards of hundreds of micrograms per cubic meter and transport times of a couple of hours. The current system does not account for what happens to the smoke after 3 hours time. So I think there's certainly opportunity to strengthen the system. And that may be part of the reason why some cities are impacted. Oh, and you have a second question. I think there's tremendous opportunity to improve communication. I mean, now that we all have smartphones in our pockets, if we could link up the plume forecasts that the state is running and distribute those quickly to people so that people with asthma or sensitive conditions could know areas that they should avoid on a particular day, I think that would be a great thing to do. An app or web developer could certainly have an impact here.
Hi, Chris. Nice talk. I just a simple question because this is not my area of work. How do you go about measuring the emission factors? I mean, how do you calibrate your emission factors?
So some of those will be from lab studies where, and a lot of those are from lab studies where people will go out, collect biomass, take it into a lab, measure its mass, burn it, measure the emissions with the sorts of equipment that Cassie and many others use. And then, so that's a lab study. You can also go out and do that in the field to some extent, where the Fire XAQ campaign was part of this, where we flew the aircraft, and I didn't make the chemical or aerosol measurements, but plotted through the smoke plume, and you can measure the total amount of carbon that has been combusted and measure the concentrations of NOx and other species. So field and lab studies both contribute.
What's the typical uncertainty associated with these factors?
Yeah, so something I didn't have time to talk about was it depends on the species of interest. What we have found is that for carbon monoxide, the main uncertainty is how much land area is burning or how much vegetation is burning. For other species like ammonia or NOx, the dominant uncertainty is those emission factors, not the amount of material that's burned. So the answer to that question depends on which chemical species you're looking at.
For example, organic carbon, which we estimate, there will be uncertainty not only in this environment, there would be uncertainty not only with respect to just the measurement aspect of it, but also, you know, your meteorological conditions and even across times. So, is that orders of magnitude or just a few tenths of percentage?
I would say in the range of a factor of 2, sort of factor of 2 to 4 would be a sort of general ballpark number.
All right, thank you.
Okay, we cannot run out of time. So next, welcome for questions for Cassie.
Thank you for your talk. My name is Wei Xin from University of Miami College of Engineering. Since you talked about this specific algae toxin that exists in air and has some great impact on health effects, so my question is, how do people or professionals take any strategies, mitigation strategies in practical to this specific algae toxin, since you introduced the filtration method, and I'm wondering if people take most application in filtration method or others. I'm not sure.
Yeah, that's a really good question. I mean, I think, you know, the filter, the air, the phase that we found in the AC filters will certainly filter out a lot of the toxins. I mean, I think the thing to keep in mind with the AC filters is getting that high performance rating and also changing it out frequently, right? Like the higher the performance rating, more frequently you have to change it out. And, you know, I think in terms of what people are doing now, I think in terms of these cyanotoxins, there's just been a lot of question about whether they're in the air in the first place. So I think there's been a lot of question of, should we do anything? There's been a lot of anecdotal evidence. When we started doing a lot of this work, as I showed you, most of it was done in people's backyards. So people who were concerned, they contacted us. We said, okay, we'll come in and we'll measure. But I think there's also just been a lot of confusion about what are the exposure routes. So what we found is that yes, the masks and the filters work. In terms of occupational exposure, I know that it's something that some other researchers at UM are continuing to look at. So Alberto Von Martinez and Kim Poppendorf, who actually did the mass spec work that I showed, they've been continuing the monitoring and seeing how people in different occupations are being exposed and what they can do to monitor that exposure and limit that exposure. But I would say, at least from our studies, the same measures that we're doing for COVID would work for preventing exposure to these toxins as well.
Thank you, Professor, for the very interesting topic. I'm a student from University of Florida, and you use a fruit fly model to. So I was curious, like how you translate the dose to like human exposure. Like, can you? Thank you.
Yeah, so that's a really tricky thing. I'm sure Grace, I could probably give a better answer than I can, because that part of the study was really designed by her. But the idea is that fruit flies actually have respiratory system that isn't terribly, that has some analogies to ours. The real key though with why we use the fruit flies is because you can see long-term like chronic health impacts show up on a shorter time scale. If we had used a different model, it would have taken us years or even decades to have seen some of those health impacts. So that's why we chose that model. You know, I think in terms of scaling it up to humans, that's going to take some work, but I think in terms of the fruit flies, it's at least giving us a clue as to, you know, whether or not these toxins are having that kind of impact. We know about the tumor promotion though, actually, because there was a couple of cases where diabetic patients who were under dialysis were having issues where they were getting tumors that were showing up in their livers, and it was found that the waters were contaminated with microcystins. So that's how that part of the piece of the puzzle was discovered. But in terms of the other effects like neurodegenerative disease and all that, I mean, that's still something that's very controversial, and it's also a big and very active area of research. I mean, a lot of those exposure studies have used oral ingestion to look at those health impacts. Whereas the airborne, exposure is something that's very new. And that's something that's been very underexplored.
I can say thank you was really interesting area. I was wondering when you encourage the use of masks and filters, apart from the efficiency, how long can it last, you know, without being a problem? Because I imagine that some of these microorganisms
Yeah.
that are hydrophobic, they would love the environment of the filters.
Right.
So they would grow, they would generate something that come real, otherwise I'm coming back into the house. Or so how long will that efficient? I don't think efficient in not only collecting the particle, but also no release anymore. How efficient they can be and how long they can last in the house.
That's a great question. I mean, I think that's something that if I were to do a follow-up study, that's what I would look at. And also, I think there's also been some really nice work that's been done, looking at how long these toxins last in the air before they undergo some sort of like oxidation reaction, and they change chemical form. Right, so I think that's sort of the question is it's kind of comparing the time scales, right? Like how long do these things last before they undergo chemical degradation versus how long are they viable for? How long are these toxins present for on these filters? I agree. I mean, I think at least for the face masks, probably changing them maybe daily would be a good idea. For the AC filters, that's definitely something to think about. And also in terms of, you know, the higher the filter performance rating, the more frequently you're gonna have to change out those filters, right? So that's also another consideration as well. I think that's something that could be the subject of a follow-up study.
Thank you.
Maybe someone will ask me first and then Dr.
So just a quick follow-up on the food fly model that you chose for the study. Did you consider any other, for example, in vitro tests to look at the toxicity of these microsystems at all, or that's already been done and in fruit fly model is probably more promising to look at?
Yes, we've only really considered the fruit fly for a few reasons. The first is, again, that short lifespan, but also, there have been studies looking at ingestion of microsystems and the health impacts. So we already knew something about how this animal model would respond to these toxins. We just basically changed the exposure routes between, you know, ingestion versus aerosolization when we did these studies. But I do think that there can be some follow-up studies that can be done, maybe even with like cell cultures, you know, like lung epithelial cells.
Yeah, that's kind of what I was.
Yeah, no, that's something that we had thought about. Is just for this particular project, as you saw, most of it was led by undergrads, and that's because it was really like a bootstrap effort to,
Okay.
yeah. Joe, did you have a question?
Yeah. What is the size distribution of the particles?
Yeah, so for the size distribution of the particles, we mainly saw some micron particles, so 100 nanometers and below, but I will caveat that by saying that our size distribution is really skewed by the way that we were generating our particles, right? The bubbling mechanism that we were using to generate these aerosols. In terms of looking at them in the natural environment, I think that would be a very challenging question to answer. Mainly because, you know, you're making these measurements in your lakes, and there's other sources of aerosol that will probably impact the size distribution of what you would measure in the ambient environment.
Yeah, but don't you have specific tests, colorimetric or otherwise, you use a cascade factor or something like that?
We haven't done anything like that. So a lot of the sampling that we did to measure these toxins was using battery operated samplers. What we were after in this case was we wanted to get spatial distribution to see what communities were being most impacted by the aerosolized toxins. So I agree. I mean, I think sort of the follow-up where I would see this work going is I think the size distribution of the toxins is a really pressing question. There's been a couple of studies that have looked at that for brevetoxin, but not much in the ambient environment for microcystin. And I agree that high volume sampling at like dedicated sites would be the way to go. I mean, I think the biggest issue that we faced was that most of the interest in the sampling came from citizens. And so we need to basically to find, those stakeholders that would allow us to deploy those high volume samplers for long periods of time. And also from our spatial maps, we now have a better handle on like what communities we see are most impacted. So now I think if we were to go back, we have a better idea of like what areas we would target to do that high volume sampling. But I agree, that is definitely the next step.
But it was my experience was, well, when we had children were young, we often go to Sanibel. And it's my sense that really, once you got away from the beach, you know, you didn't have to go very far before your own detector told you that, you know, that the impact had decreased considerably.
Yeah.
So it was, my sense was that they're relatively large particles.
Yeah. Yeah, no, that's a good point. And I think, you know, I think there has been a lot of work trying to characterize whether the toxins are intracellular or extracellular, right? Because that would also factor the size distribution. We actually had a really good undergrad. I didn't mention her on the slide, but she did a senior thesis on looking at the microcystin. She ended up following up to do her PhD at UNC. Her name's Haley Floss. She's actually been characterizing the size distribution of these toxins in estuaries in North Carolina area, and also looking at whether the toxins are within cells or external from the cell. So, so for those of you who are interested in that, in some of that follow-up work, I would check out some of the papers by Haley Floss. She's done some really, really great work trying to characterize that.
Okay, we also run out of time. So, next, welcome for questions for Joe. So I have a question. I think terrific photo first. Amazing. So I have a question is, what are the origins of these sample tests? Are they just due to dry weather, or there are some other sources?
That is a major question today, is what are the specific sources? And there are some, I mentioned that there are generic sources. Dry lake beds are spectacular. If you look at satellite images, you can often see that there are very specific hotspots that are generating, you know, unusual amounts of dust. But when you try to place it in the context of just sort of the rest of the sources, which cover much large areas spatially, it's difficult to separate those different sources. And there's also the generic question spatially. There are regions of Africa as a speaking of geological scales that are much more active than other regions. And I showed you the map of emissions, and you could see that there was a model appearance to it. So and I mentioned the use of isotopic tracers to try to get fingerprints. And there is work now that shows that you can see changes in the isotopic signatures, which sort of can be related to certain areas. The problem is at a very fundamental level is what's going on with the sources in general at the surface, the character of the surface. I mean, when you see models, they work with soil profiles that they obtain that were obtained for soil agricultural purposes. They're like, you know, if someone goes along and have a shovel and a bucket, and every so many tens or hundreds of kilometers, they take a sample. And yet the dust is not coming from the soil profile, it's coming from the surface. And so the question is then, what is the surface that is most active, and what makes it active? And that has to do with soil moisture covered by vegetation, disturbance of the soil surface, and wind, and the geomorphology, which can generate turbulent eddies, which can more impact the surface. And you know, with many people that look at this at ground level, in order to generate dust, it's often not easy. You have to get particles impacting the surface, bigger particles, to break the surface and then start to. So it's a complicated process. That's why when they look at the 16 models in that comparison, one of the reasons why they got very diverse results is because one of the reasons is the very specific nature of the dust generation process, and how well you think, you know your services on a global scale. That is a non-trivial job. So, yeah, it's going to be tough before the models can really get that down solid. I mean, the meteorological part of the models, once you get stuff in the atmosphere, the models pretty much do the same sort of thing, you know, the removal processes enter into it, things of that nature, but it's the source activity, which is really the limiting factor.
Thank you, Joe, for your talk. So, you mentioned about these dust models, I mean, at the radar side. So I wonder if there are similar, like, detailed analysis in South Florida, is that happening?
I'm sorry, if there what?
Measurements, these type of dust measurements in South Florida?
You mean source measurements or?
These types of measurements, like measuring dust, filter reflections and.
Oh, yeah, we do.
Measurements.
Cassie's doing, I should say, yeah. Yeah, we're there, and we have, there are a lot of people that operate with us doing different things, and when I show the slides, I mean, I refer to papers and their cooperating groups who work, you know, we've done extensive work in Houston that I've never done research in Houston, I didn't use it, but they have very specific interests, and so the way it started out was they took some of our samples from Barbados and used that as a reference to comparison. When I showed the plots of the isotopic signatures, and I have some also chemical elemental signatures that, you know, are maybe informational as well. But so a lot of the work that we do has been in that context. And there's a lot of other work, and Cassie is very familiar with it, other groups, a number of people from German groups in particular, made use of the site. The work that I showed with the particle size distributions was by Harrison, who was interested in measuring the ice nucleating properties of African dust related to mineralogy and things of that sort. So the site it has been widely used, and with the developments now that Cassie has initiated with augmenting the site, she received a major grant to do that. We expect there is going to be a greater diversity of groups using that facility, and it goes beyond the chemical physical measurements of the aerosols, but actually the relationship to the atmosphere, and there are LIDARs, and there's a whole spectrum of instrumentation that we've used and other sites have used in Barbados. So Barbados is playing a critical role, and because of its long record, but also because of the fact that it's been widely used to get at some of these characteristics. And I point out that there is a very good aerosol site also in Puerto Rico. Olga Mayol used to be on the faculty at the University of Puerto Rico. She's now at Brookhaven. And I don't know what's going to happen to that site, but it's a very well instrumented site. And that's been used for research studies as well. They're interested in things such as the optical properties of the dust that measure or filter, biomass burning impacts, things of that nature. And of course, the work we do here in Miami, where you know, we don't have a long record as in that detailed sense as we have at Barbados. So we're hopeful we get something going again in South America. We had a relationship with a group at NKN, and where we much focused on the possible impact of African dust as a source of nutrients for the Amazon basin. But you know, I started that work in the late 1970s as the first paper. But until recently, there really has not been much work in that regard. Mostly been speculation, and a lot of it is wrong, I think. But it's still, you know, and Cassie has published a number of papers now on various aspects, including the possible impact of biomass burning products transported from Africa to South America. So yeah, it's an open program we have, or I should say Cassie has. I mean, I had it when I was in charge, and Cassie is doing a spectacular job in that regard too. So if anyone's interested in pursuing things of that nature, you know, I'm sure feel bad to address those issues with you.
So my other question, I think you briefly covered that in your talk, is about the climate impact of these dust aerosols. So are there, let's say, systematic studies showing that these dust are affecting cloud formation? What type of cloud formation, precipitation, and then overall in South Florida or in the equator region?
No, not really. There is a group, a German group, that has a very, spectacular, research station on Barbados, about a kilometer south of us on the coast. And they focus primarily on the meteorology of the region. And they have a variety of instrumentation, including various types of LiDARs and things of that sort. So they're very much interested in that possible role, but they tend to be skeptics of the role of aerosols. But that's their viewpoint. But my point is that there is extensive instrumentation there, and hopefully when the people like us interested in the physical properties of aerosols and those people get together, maybe someone come up with that. But so yeah, it's certainly of interest there.
I have a question about measurements in the air above the ground for those long transport buses. Can you make some comments on that? Have you done any measurements, monitoring stuff?
Well, we started out making aircraft measurements in the late 1960s, and of course there have been a number of campaigns since then that involved aircraft, but the LiDAR, we had LiDAR at the site, and also we have a LiDAR site here in Miami, which provides vertical profile, and normally and maybe one of the talks that will be presented some of that information. But it remains a major problem. That is the role of the Saharan aerosol layer and the propagation of dust across the Atlantic is still, there's a talk about atmospheric rivers of water, but the Saharan aerosol layer was an atmospheric river of dust. I should have coined the term, but it really is. It's quite striking. And I showed you one slide, but it's really spectacular. Where there are no clouds, it's like a tabletop. I mean, just it extends in all directions as far as you can see, and it's really quite remarkable because of the inversion of the top of the layer. But it's the inversion at the bottom of the layer that really is a critical issue in the transport across the Atlantic, because normally you would not expect things like that to survive over that distance. So most of that, a lot of the removal takes place in disturbances where you have relatively deep convection that can break through the layer. And there's a lot of interest in that regard. There's a lot of interest in the role of African dust and the relationship to tropical disturbances and hurricanes. And the Hurricane Research Laboratory is located across the street from our school, and Jason Dunyan he's been looking at this problem for some time, and there's an indication that the presence of these Saharan air outbreaks suppresses development of tropical cyclones and hurricanes, but it's not clear whether it's the aerosol properties themselves or whether it's the role of the layer, the Saharan aerosol layer of the deep inversions, which intrudes into the circulation of the tropical disturbance and breaks up the circulation. And that may be the dominant role, but there's still a lot of discussion that's going on about that. There's actually been relatively little detailed work of the role of dust within such systems that's been carried out. At least I'm not aware of any recently, but it's always part of the chatter amongst the hurricane community as to that role. There is a link between the aridity of North Africa and tropical cyclones, in which you could then, through that factor, relate to dust. But it's not, again, it's not clear whether it's the dust itself that has that effect. The dust also has a role in reducing the direct solar radiation to the sea surface. So the sea surface temperatures are slightly cooler during dust outbreaks than when the dust is not present. So, you know, it's a complex picture, and there are many threads pulled out.
Okay, let me double check. Do anyone from or joining from Zoom have any questions? Okay, so anyone has any question to any one of the speakers? So feel free to ask. Okay, no, if no, then I just.
It's more just like a quick comment, the question about the aerosol cloud interactions with dust. Actually, Haley Warrior has a nice paper that just came out, I think maybe today. Where we looked at CCN properties of dust versus African smoke. During wintertime, dust intrusions, and we actually see a really strong role for the smoke in controlling CCN activity. So that paper just came out if you're interested in that. Sorry, shameless plug for my paper.
I'd like to make one more comment. I mentioned the health impact of the aerosols mentioned in several contexts, and dust gets, when you talk about PM 2.5, PM 10, and health impacts, we still do not have a good picture, or even a poor picture. Well, we have a poor picture of the health impact of dust, but it's a question whether it really does have whether the PM standards really apply, because the PM standards were set up not for any specific component of aerosols, but just studies urban areas, populations, and changes in the hospital attendances or occurrences of this or that or the other thing that's related to mass measurement. But, you know, the African dust, or mineral dust in general, is very different from your typical urban aerosol. So it's not at all clear that's whether those standards are relevant. And I mentioned the fact that, you know, the asthma is very big in the Caribbean. I mean, asthma rates in the Caribbean are just as high as they are in the continental US. And in the early days, after I started the research on dust, there was a lot of talk about whether dust was impacting asthma rates in Barbados. And I knew people at the hospital, and they said on dusty days, there were a lot more people showing up at the asthma clinic and all, you know, that they noticed that when there's a lot of dust, that there were a lot of people in the clinic, and they associated, you know, the increased attendance with that. And we did a paper on pediatric asthma in Barbados using our actual mineral dust measurements at the Barbados Tower and looking at the attendance rates. And we found no relationship whatsoever. But when you get a epidemiologist to look at the data, and they plug a lot of other things into it, and they come up with magic numbers, but it's very clear. We looked at the big spring peaks of dust, like I took you in Martinique, where there's a big spring peak isolated in time. And there you could see in Barbados, under equivalent conditions, you couldn't see any change in attendance at the clinic. So my conclusion was that retrospectively, when people at the clinic had a high attendance rate, they would look out the window and say, "Oh, it's very dusty today." But they didn't look out the window when the attendance rate was low. So that's how they developed the relationship to African dust. But that's certainly a prime topic for research.
Okay, thank you. So several announcements. So first, there will be a group picture right after this, right? And also there will be a campus tour. So please stay tuned. And also today both lunch and dinner are provided. So you can stay here kind of late today. So I think that's it. Thank you. Thanks a lot for this morning's speakers. Then I will have
Yeah, so we're taking one picture at the stairs or between the second and third floor. So, yeah, so people are spread and then we can take last picture. All we can do is back activities with you. All right, let's welcome you back.
Thanks. Everyone, thanks again for the warm welcome and warm invitation. It's been a real pleasure to see some familiar faces, people that I enjoy working with, some new faces too, and looking at opportunities that we can kind of work together, especially in relation to this EMF rate. So for those of you who like salad, my title is a little bit of a word salad, and but hopefully we can take away some useful tidbits about this deployment. So this is work done out of funded by Department of Energy, specifically 3 programs: atmospheric system research, user facility for ASR, which is ARM, atmospheric radiation measurement. We'll talk a little bit about that, and then also internal funds for Brookhaven National Laboratory. And this is work done in collaboration with several other national labs, Argonne, Sandia, friends and colleagues at Aerosol Dynamics, and then also our computational science division. So my presentation today will be kind of 3 stories, and they may not seem related, and sometimes they feel like they're not related to me when I'm working with them. But I hope I can kind of show you the various threads that connect these 3 different projects and give you kind of a sense of the couple model, observation, and instrumentation development work that we're doing in our group. So first 15 minutes, I'll be talking about fast simulation on MODEX 2.0. Right. This is an internal effort at Brookhaven, really at developing a computational framework that integrates models and observing and observations to do uncertainty quantification geared toward optimal experimental design. And this is a topic that I think we're familiar with, but doesn't really get often a lot of attention or funding to do. So hopefully I can make the case that there is a way to do it. It's not easy, and hopefully can make the argument that it's going to help us be more quantitative and more optimal in how we use resources to design instrumentation, observing systems, etc. The next 15, I'll be getting into the 3rd ARM mobile facility. This ARM user facility that Yang introduced will give you updates on where we're going, how we're considering it, how we're going to instrument it, and opportunities for the community to engage with this deployment. And then the last third is kind of like, oh, this, after I pay the bills for the first 2/3, this is the fun stuff for me, talking about new particle formation, right? This aerosol process that happens in the atmosphere has climate impacts, and I'm talking about vertically resolved and talking about instrument development, some field measurements, and then connections and opportunities related to the AMF rate. So the DOE's mission, right? DOE's mission and mandate is to improve climate models. Right. And for those of you who are familiar with either running a climate model or interpreting the results, there are barriers and there are challenges with using climate models, right? One of them, I'm not saying this is the biggest one, but this is a challenging one. There isn't a lot of feedback sometimes between model uncertainty and then what we're measuring and how we're measuring. So this little bit of a mess is meant to kind of illustrate in practice, what do we do in the field? For those who make field measurements, well, we design instrumentation, we make observations, we wait a year, maybe 2 years before it goes into a model. Right? Let's all be upfront. Sometimes that's how long it takes. You run the model, it outputs, and by the time you get model results, you're already done making your observation. Now, this is not true for every field site. Thank goodness there are continuous field sites, right? Where you get some feedback. But for often a lot of campaigns is you make measurements for a year, you wait a year, you model it. Then you figure out what you are modeling. And so, you know, there's uncertainty quantification, there's scaling for spatial scaling, and oftentimes a lot of these connections are ad hoc. That means they happen when you get funding to do it. Right? You think about your proposal cycle, and each one of these is basically a proposal effort. So best case scenario, you have 5 years before you learn anything about it sometimes, right? So what this often leads to is a big time lag between measurement and discovery. right? And as a corollary, oftentimes when you design an observing system, when you design an RMO facility, you're doing it ad hoc, right? You're going by whatever people have done in the past, you're going by your intuition, right? Nothing wrong with that, but it's oftentimes very hard to connect that with model outcomes. So within DOE, there is a concept called MODEX. Right? What is MODEX? It's model experimental closure. It's a concept that has gotten some traction within DOE to enable coupling of models and observations. And so when you take a look at this, it's a little bit clearer than what I showed earlier, right? Where let's say you're making measurements, you upscale those measurements, feed them into a model, you do uncertainty quantification, get information from experts and your knowledge, you do the UQ, and then this is supposed to tell you, okay, what are the new measurements we should make to improve model predictive uncertainty? Right? But I will tell you, oftentimes this is not fully realized. It's not even partially realized, right? For at least one very good reason. We don't model what we measure oftentimes, and we don't measure what we model, right? And so getting this type of closure is very challenging to do, and also related to the fact that our the spatial and temporal scales are really mismatched between models and observations. So what are we proposing to do, right? And so our approach is, well, what we're going to do is we're going to take models, uncertainty quantification, scaling, and observations, and do them synthetically first. What does that mean? That means we do all of this work that you would do after a campaign starts, but you do it on the computer. You simulate it. So you simulate observations, you simulate instruments, so that we can get an understanding about where the bottlenecks. So we use existing tools, uncertainty quantification, we use machine learning and artificial intelligence to run our models, because oftentimes, I'll get into this later, we need to run a model about 10 to 50,000 times in order to capture the measure of uncertainty, right? And we use something called OSMOS, Observing System Simulation Experiments. So these are concepts that have found a lot of traction within the satellite community, where they want to simulate a satellite in order to see what that measure. But I propose that we can do this also for aerosol measurements, especially if we want to capture spatial heterogeneity in aerosol. So our approach is, well, we're going to do all of this stuff pre-deployment, so that once we start the deployment, it's as straightforward as flipping a switch, where now, instead of working with synthetic data, we're working with real observations and real instrumentation. And the idea, the rub is that just because we start the deployment doesn't mean stop doing this portion. We still do this synthetic portion, informed by the new measurements that we're getting. And this type of coupling of pre-deployment and post-deployment co-design is going to allow us to better optimize our investments for these observing systems. So with all that being said, just because you have a computational framework, you need a science question, right? So in this case, one of the science drivers is looking at, well, what are the drivers of VOCs, or biogenic volatile organic compound emissions in the southeastern US, and what are their land atmosphere effects? So this is just another kind of concept schematic showing one of the climate aerosol processes we're interested in deploying and studying with the AMF3. In this case, we're very much interested in, well, what are vegetative emissions in the Southeast United States? What various gases are emitted? How do they react photochemically in the atmosphere? And then how do they eventually become aerosol that can either become clouds or have impact directly with radiation? And so taking this as an example, we then need to choose a model. So I recognize that this is an aerosol community, and it would be great to work with an aerosol model. And I'm very willing to answer questions about why we're not working with an aerosol model initially. But for the purposes of this project, we're working with a land surface model, E3SM, using the Megan model for emission of VOCs. This model captures a lot of surface atmospheric change, radiation, energy, ecosystem cycling of CO2 and water, and importantly, it also captures biogeochemistry, specifically emission of VOCs, vegetation, and biological aerosols. So this is our kind of our model for doing this initial type of model observation. So getting into a little bit about if we're developing a computational workflow, what does the workflow look like? And so this is schematic meant to emphasize that, well, When you run a model, what do you need? You need initial conditions, oftentimes to also include met forcing or reanalysis. We need to define where we're going to run the model, and we need to define what are the parameters. You take these two activities together and you generate ensembles, or the number of different simulations you want to run in order to understand a process. You execute it on a high-performance computer, you get your simulation output, and you do sensitivity analysis and uncertainty quantification. You compare with observations, and then you fuse them somehow to do model observation, constraint compares. We call it MODEX 1.0. This is just a generic sensitivity analysis. This is what oftentimes a lot of us do for modeling. What is kind of novel about this effort is that we don't stop with the sensitivity analysis. We take our data model, fuse data, we calibrate the model, and we generate synthetic observations to inform how we make our observing system designs. It's this feedback informed by our sensitivity analysis that is really going to give us a chance to quantify why we're setting up our observing system in the way we are. So this is just an example of some model data. So the model data is in the ensembles are in green and our observations are in black. And this just shows you the range of, in this case, latent heat flux that we're simulating over the span of several decades. And just to give you a sense of this is what our model observing system comparison is beginning to look like. So currently we are here, right? We're in this part of our project. So we've done some initial ensemble runs. We set it up on BNL supercomputing resources. And what we want to be doing next is calibrating our model, doing the optimal experimental design, and then directing these efforts towards the AMF3. So I just want to go over what we're talking about when we're talking about OSSIs. And the idea is that we want to do MODEX on the computer before we need to deploy a resource, right? So this optimal experimental design is, well, if we have a certain design goal, let's say our design goal is we want to reduce uncertainty and radiative forcing by 50%. That should dictate and tell us how we design our observing system. And if we want to reduce model uncertainty, we need to stimulate the effect of putting data into the model. So that's why we need to use synthetic data. So let's say we have 3 sites measuring some aerosol quantity of interest. Let's say this is PCN number concentration, right? We take these 3 sites, we take our time series and we calibrate a model, and then we get some spread in some parameter. Let's say hygroscopicity, let's say activation efficiency. So the design question is, if we want to put in a 4th site at one of these 2 locations, location A or location B, which one do we choose? So the idea is that we want to select the location whose data, if we measured it, reduces model uncertainty. The problem is we haven't measured data at any of these sites. So we have to simulate the data. And we do that using these observing system simulation experiments. First step is we run our model, get a time series. Then we have to simulate the synthetic observation by putting in unmodeled variability, model bias, instrument error. And that's represented by these kind of black dots drawn from our model. But the other problem is, well, we're uncertain about what our data will be because we haven't measured them. So we need to simulate uncertainty. So we generate ensembles of these simulated data. And the idea is that when we run these ensembles, we get different kinds of model uncertainty results. Site A, we do the same thing for site B. And the idea is that, well, we pick the site that has the greatest average uncertainty reduction. In this case, it would be site A. And then this is kind of a simple example of telling us where do you put another measurement site if you wanted to reduce model uncertainty. And so our idea is that to develop a framework for model experiment integration, and the idea is that we can use this to analyze real data and design observations. So our target for this effort is the deployment of the 3rd Arnold Gold facility in the Southeast United States. This is an aerial image of the Bank National Forest in northern Alabama, and some nice pretty clouds to kind of give you a sense of, well, this is kind of our spatial domain that we'll be working in for this 3rd Arnold facility. And this is going to be a target for our MODEX 2.0 activities. So I'm want to get into a little bit about what is an ARM mobile facility and what is ARM. So ARM is atmospheric radiation measurement. It is a DOE user facility. Right? They're tasked with making climate observations of aerosol precipitation, surface energy radiation, at different observatories around the world to improve Earth system models. All the data is publicly available. And ARM has both fixed location sites, so Oklahoma, Alaska, Eastern North Atlantic, and also what they call ARM mobile facilities, places that have been deployed to oceans, to both poles, and in this case, for the third ARM mobile facility, we're going to the southeast United States. So these are a sense of kind of measurements that are made from an ARM mobile facility. This gives you kind of sense of what the assets look like. So there are sea painters, there are radars, there are upward facing radiometers, and also towers measuring atmospheric state, energy, aerosol, clouds and precipitation, as well as aerial measurements. I'll be getting into a little bit about this here as well. So why are we going to Southeast United States? So in 2018, DOE held a workshop. So they identified this region as being very interesting and a high priority because of abundantly locally forward salad convection, right? This area has a lot of severe weather, right? If any of you were traveling this last week in this region, you might have been impacted by some severe weather that was in the region. Northern Alabama got hit really hard with some severe tornado outbreaks. So this is a region that has a lot of convection. It's a region that has a lot of vulnerability when it comes to resilience against severe weather. Unsurprisingly, there's a lot of vegetative driven biogenic conditions. And what makes this area so challenging and interesting is that the strong coupling of the land surface to the atmosphere. We expect a 5-year deployment with fingers crossed deployment beginning fall of 2023. But if you want to talk to me about when that will more realistically happen, I'm talking afterwards. This is a joint funded project by both our science program and our user facility. And where we put the site, how we configure it, how we instrument it is determined by a site science team that I'm leading and site operations. Our core team has leadership that cover aerosol, convection by Scott Giangrande, and land atmosphere interactions by Sean Serpent. The rest of our site science team has members that you might be familiar with, covering aerosol, biogenic aerosol, convection, shallow convection, climate modeling, as well as forest canopy impacts on boundary layer development and turbulence. So our team was designed to be able to look at land, aerosol, cloud interactions in this particular area. So I'm just going to go briefly over some of our science drivers. So don't know how many convective scientists are in the room. Show of hands. Yes. So because there's a lot of severe weather within this region and a lot of abundant convection, we're very much interested in setting up our observing system so that we can see convective cloud onset. So convective initiated how these severe systems form. We want to be able to observe their transitions thousands of feet. And then also deeper convection and corresponding precipitation and impacts of deeper convection on things like aerosol transport. Our aerosol science drivers are very much interested in, hey, what are the processes that control the budget of aerosol in the boundary layer? So we're interested in particle formation, transformation of VVOCs, CCN activation, as well as impact of aerosol radiation. And then kind of underpinning and grounding both of these topical areas are land atmosphere interaction science drivers, or LAI. So very much interested in what are the service controls on water vapor flux, energy flux, VVOC emissions, development of turbulence within the boundary layer, and of course, two-way interaction between vegetation, clouds, aerosol, and the radiation. So I would be remiss if I didn't kind of explain why are we going to know. I recognize presenting to a group that is in Florida, and I fully expect to get questions about why not Florida. I'll answer those questions. But here's some of our criteria for why we decided to go interior to Northern Alabama. We wanted to avoid the coastal region and similar complexities. I'm not saying that this is necessarily bad, but there are other deployments that are designed for coastal. right? We wanted to focus on interior. We want to be in representative terrain. That's in quotation marks because how do you define representative? What are your spatial scales? Program managers like to ask this a lot. And from an aerosol perspective, we want to be in a place that has representative air mass. What does that mean? So my approach was, it can't be too clean. It can't be too polluted. We want to sample a range of both of those conditions wherever we site. And again, we want to be in a place with frequent clouds and frequent showers and convection. So what we did during the pandemic is, because we couldn't go anywhere, we leveraged some expertise for people making maps. So doing geographic information system analysis, where we take all of our criteria and we build map layers. So this is the resulting map layer, where green regions are places that met our science criteria and our operational criteria. We requested 3 non-collinear supplemental sites, and we kind of ended up looking at Northern Alabama because high frequency of convection. We have proximity to many potential partner facilities. The terrain is okay, the forest is good, and we get a range of anthropogenic and biogenic conditions. We did a number of site visits over the past 2 years. We built up local partnerships. We engaged with universities, networks, and importantly, we evaluated logistics. Things like we have power, we have communications. Are we somehow interfering with military activity, ignores? And then things like where do we put supplemental sites? So typically, where do we put a tower? So this is an overview map of the Bancan National Forest where we are putting the main facility. So this shows you where we're going to put the main site, this black square, one from the Boston Tower here. And here is a zoomed out map of Northern Alabama showing where our main site is, as well as various supplemental sites to give us spatial coverage and give us opportunities to look over the site. So our plan is this fall, the main site becomes operational, and then in FY24, we establish supplemental sites. Again, an overview of what the main site looks like and some of the facilities installed. So we plan to have space not only for instrumentation, but also guests. Right? A site is only as successful sometimes, actually a lot of times, as the guests we can visit and have room and space for students or other investigators. So we're going to have a guest instrument facility where students can engage and interact with the measurements, as well as our aerosol, various aerosol, radar, and profiling instruments. And there's also areas for you, if you wanted to, or if it makes sense, to drive up an RV with your instrumentation, a little mobile trailer, right? So we have power hookups here too. And this is what our aerosol observing system looks like on the outside. And this is an image of our 10-meter. So we're going to be making basic measurements of aerosol water uptake, chemical composition, optical properties, size distribution, and trace gases. So in terms of our baseline measurements, I wanted to put this slide up because I wanted to give you a sense of the kind of instruments we were looking at. So this is my shout out to some vendors here. Let's talk a little bit later about how we can execute or improve on some of these deployments, as well as options for distributed sensing. And I put in a little shout out to SET because our measurement categories were so close, like 75% of the way there. So I'm making a strong pitch that you add additional instrumentation so we can meet and align with the SET measurement network. That also makes measurements of trace metals in the air, along with the measurements that are being made here. So these are all baseline measurements, right? This is the stuff that's now operating teams for the 5+ years. We're also going to have a forested flux tower. So for ARM, this is new and probably really scary for them. So we're planning a 140-foot flux tower inside the forest, where we'll be making measurements at the top, above and below the canopy, and at various sites of the surface, along with planned measurements of basic meteorology, trace gases. I've also put in requests to measure biological aerosol, especially any biological aerosol being emitted and injected from the forest canopy surface, as well as making aerosol flux measurements and biogenic VOC measurements as well. So this is again kind of to give you a preview of what we're planning after the main site gets established. We want to establish 3 supplemental sites in this triangle configuration. They're about 60 to 65 kilometers, and that distance is deliberate. We're going to be making measurements of atmospheric profile properties. We're going to partner with University of Alabama, Huntsville, using their radar assets. We want to develop an aerosol sensor node network. And it's designed to capture aerosol spatial variability within this domain. Obviously, we can't deploy full AOS. That's a non-starter. So this is again, my outreach to the instrument manufacturers here about thinking about and coming up with ways to develop lower complexity, lower cost aerosol measurements so that we can capture spatial variability in a low complexity way. There will also be aerial measurement platforms, so TDS, uncrewed aerial systems, as well as anti-cloud precipitation radars located right about here. So getting into this aerosol sensor node network, you might be wondering, why do we need to have a network? Well, quite simply, where we are in northern Alabama, there are a lot of sources and sinks. And so what we're measuring in the forest, we're not going to capture a lot of perhaps any signal as well, signals from urban sites, as well as in the agriculture. So this is a typical global climate grid cell showing maps of canopy fraction, the emission of nitrogen containing aerosol, as well as emission factors for isoprene, which is a prominent EBOC region. So already you get a sense that even with this 100 kilometers per grid, there's a lot of emission. Right? We want to capture that because of its impact on regional climate. And this image on the right is an image of what this aerosol sensor node could look like. So this is an image of an enclosure with several POPs units inside, deployed as part of the POPsnet network to the Southern Great Plains. And so these are the kind of instruments and kind of design considerations we're thinking about, right? How to build low complexity, low operational burden types of instrumentation. So if there are any ideas, I am all ears to hear about them. And then again, because we have opportunities for aerial platforms, we are planning to deploy aerosol instrumentation on some of these uncrewed aerial systems or drones and connecting these measurements of aerosol with remotely sensed properties of the forest. So the structure, health and stress of the trees, physiological traits, and fusing all these data together to come up with a quantity, a fused quantity that can be used either better for training models or reveal coupling between the biosphere and the atmosphere. So this is my abrupt change to now getting into some of the research, some of the aerosol research that I have been doing and hopefully continuing to do at the AMF3. So I decided just, something we've preached to the choir, which is to say that a lot of the aerosol that we're looking at has different sources and they have different sizes and they have different climate impacts. And importantly, they have different sampling challenges. I would posit that trying to measure coarse mode aerosol is really the Wild West. Like in my PhD work, I was focused on measuring one elevator aerosol. I thought that's hard. It's not that hard. Measuring this is really, really hard. It's still hard, and there's still a lot of knowledge gap within the community. And which kind of explains the motivation for why we also want to be measuring biological aerosol with the AMF as well. So this is just to kind of seed some ideas within this group about what things are exciting to measure and are really hard to measure and would really advance science in AMF3. So within our group, right, we're interested in looking at aerosol effects. So we're looking at aerosol, aerosol part formation, biomass burning emissions, impact on radiation, and then also cloud aerosol interaction. So specifically for this section, I want to talk a little bit about new particle formation, their growth and their contribution to cloud condensation nuclei. So to kind of walk through some of the steps towards, new particle formation involves the photochemical reaction of sulfuric acid, maybe some organics, maybe some ammonia and amines. They react to form, 1 to 1.5 nanometer critical clusters. These clusters then grow and grow and grow until they can potentially be the size that's large enough to be CP inactive and then they become cloud droplets. So the two big processes here are the formation, which generates aerosol number, and then also the growth. Because if these clusters don't grow fast enough, they get scattered by increasing aerosol and they don't add and they can no longer become. And the reason why we study this is that NPF can contribute up to 50% of boundary layer cloud condensation. So what's my motivation of studying vertically resolved NPF? Well, part of it is that NPF locked, followed by transport, could be important sources. Furthermore, a lot of the model parameterization of NPF are based on surface observations. That's not a criticism, that's just the reality of making long-term measurements. It's more easily done on the surface. So are we missing initial NPF, and how is that impacting our models? Consequently, and related to that is, it's really hard to make vertically resolved NPF observations. You're basically gonna put it on a plane, a helicopter, sampling on a mountain that is periodically inside of a troposphere. And the reason we're studying this is that the spatial distribution, like where NPF happens and when it happens, is probably strongly controlled by boundary layer dynamics. Right? So in this schematic from Matlab et al., they posit that during the day we get emissions from the surface. They get well mixed throughout the day. They combine with maybe long range transport. They hang out in the residual layer at night. And then the following day they react chemically and they can transport it down. And so our goal is reducing uncertainty. Right? What is uncertainty limited by? Well, there are large vertical gradients in the distribution of NPF. This is a measurement made at the Southern Great Plains, where they show elevated concentrations aloft, about 300, 400 meters, but very low concentrations on the surface. So surface measurements are missing part of it. What are the other challenges? Large measurement uncertainty, measuring NPF via SNPF, right? A workhorse standard tool for our community. So here is a model simulation of, well, what would a size distribution look like under new particle formation conditions? So we have pre-existing aerosol here, and then a lot of new aerosol form between 1 and 2 nanometers. The challenge with using an SNPS to measure this, I'm not saying it's impossible, but one of the challenges is that an SNPS relies on a neutralizer to charge a particular aerosol. Right? Usually that's not a problem, and you actually need to charge it in order to mobility classify it. The challenge becomes the neutralizer ions are on the same size as their uniform clusters. And so this represents an artifact, a measurement interference that swamps the signal you're trying to measure. So our approach is, why not use another tried and true technology? Why not use a CPC, a condensation particle counter to make this measure? And I'm going to talk a little bit about how to do that. So this is my plug to the, to this group, which is preaching required, but what we're trying to study should tell us what instrument platform we use, right? If this is what we're trying to measure, if this is pre-existing aerosol, we only need a fine CPC. If we want to measure a growing NPF, we can use an ultrafine CPC. If you want to measure the forming nucleation level, you need to measure down to 1 nanometer. And this is an image of a prototype CPC that I've been working on in collaboration with ADI. It's basically a magic CPC with a diethylene glycol inlet. And this shiny little box is the enclosure for the CPC so that it can attach to a temperature. Right. So as part of this effort, so this table is old, but if we want to deploy a 1 nanometer system on an aerial platform, we need to see what's available commercially. What are the weights, the power requirements, and other important considerations. And at this time, I chose the partner with ADI because the Magic CPC is lightweight, low power. We could put it on a 10 right? And under battery operation, you can operate for about 8 hours, right? Not bad to do several profiles in the boundary there. The challenge is that its cut size is kind of high for our purpose. So I decided let's work with this system and lower the cut size down to 1 nanometer. So the idea was to modify ADI Magic CPC because it met the weight requirements for this tethered balloon. So this is the arm tethered balloon. And the effort was, well, how do we lower the detection and how do we get information about sizing? Because the CPC only tells you number concentration for the most part. But we used some tricks that kind of speed up the sizing information. Part of the challenge, and it was really great to visit Yang's lab to see his aerosol instrumentation and calibration system set up. If you have to calibrate the CPC, we don't understand what measuring. So we use a high resolution DNA system to generate single ion mobility standards, which are mobility classified, and then challenge this magic CPC to generate size-dependent detection. So these were the size-dependent detection efficiencies under the modified conditions. So we were able to measure it down to 1.5 and 1.9 nanometers. So we met one design target. And the power draw is not bad, 15 watts, which is about 7 to 8 hours of battery power operation. Our next goal was, well, we can measure down to that size. And we get sizing information out of this space. This is where we leverage some very old school techniques, pulse type analysis. So this basically, what we basically use is we use the size of the grown droplet with the CPC to tell us about the size of the sample aerosol. And the idea is that inside of CPC, this is a simulation of the saturation ratio. Large aerosol activate at low saturation ratio. They have a longer time to grow and they grow to larger droplets. So this is cartoon large aerosol, it has this much time to grow. Smaller aerosol activate at high saturation. So they have shorter time to grow, they grow to a smaller droplet. And we use this type of size discrimination to get information about our sample pairs. So here are some laboratory results for what some of the droplet sizing looks like. So this is the size distribution of a 10 nanometer sample aerosol. So this is the droplet distribution. This is the distribution of a 4 nanometer sample aerosol, and then the distribution of a 1.3 nanometer aerosol. So we're getting some size resolution. It's not superior to a DMA, no, this is coarse resolution, right? And we would have to invert this data still to recover the original size. But this is basically squeezing outside the information. This is what it looks like from the perspective of the CPC on the end of the balloon looking down. And, this is the southern Great Plains, and this is where the CPC is located on the top of the balloon. And here are some preliminary measurements taken with this system. Just this past, not this past October, right, but 2021. This is our altitude profile, getting up to about 1,000 meters. So our idea was to be able to get above the boundary there during the morning profiles. And here's the pulse type distribution from a CPC. This band right here is our pre-existing aerosol, so quote unquote large. And this band down here is our clustered small aerosol, potentially new particle formation. Right? So we're seeing elevated apparent NPF velocity, right? That eventually will get transported down to the surface. Again, this is another measurement from the pulse heights. So the horizontal axis is pulse height, raw counts. This peak right here is from pre-existing aerosol, and these peaks are from our cluster mode, potentially newly formed particles. So all of this is just from a single CPC. This is what the integrated profile looks like. So at the surface, very low concentrations, and as we descend, we measure elevated concentrations, suggesting NPF, followed by our descent. Again, in this case, we're descending faster than the air mass is descending, so we're measuring low concentrations to get at the surface. So these are the measurements that we use to kind of tell us where NPF is happening. And then to also form high resolution turbulence resolving models about, well, can we even capture where NPF is? So as part of this deployment in the southeastern US, we want to be making some of these kind of measurements. So perfectly resolved measurements to contextualize the surface. Furthermore, it's an opportunity to explore environmental transitions. So forest, rural, agricultural, urban. We have opportunities to make vertically resolved and also surface distributed measurements and using them in high resolution models. And it also will be a test bed. So again, this is my outreach to both PIs and vendors to test emerging measurement technologies and to leverage artificial intelligence and machine learning applications for clients. So if you want more information about our deployment, you can take a photo of the QR code, and it works. And here's an overview of the Benken National Forest. It uses what the terrain looks like and what the forest kind of looks like within that region. Thanks.
All right, so let's move on to the second speaker. Okay, so our second speaker will be Dr. Pukita Tuilima. So she's the chair and professor of the Department of Atmospheric Science here at the University of Miami. So she'll be talking to us about her study on the smoke cloud interactions and their implications in South Florida.
Let's see, we should be the first slide to this. Okay, great. So we saw a great talk earlier today by Chris Moltz on fires in South Florida. And I'm going to take you a little further afield, also looking at smoke, but in a different part of the world in the Southeast Atlantic. So ending in about 2018, there were a number of pretty large campaigns in this area that were looking at aerosol cloud interactions with the biomass spreading aerosol. And in particular, I'll end up calling your attention to a armed mobile facility deployment to Ascension Island in this in about the middle of the Atlantic, about 8 south, so not far from the equator. But there was a NASA aircraft campaign, and there was also a UK aircraft campaign that ended up getting deployed out of Ascension Island. So the motivation for this was climate, and we were very interested in trying to get a better handle on the direct aerosol radiative effects over the Southeast Atlantic. Climate models varied a lot, like even in the US models, you could see an overall cooling effect and regional cooling in the one of the NASA models, whereas there was pronounced warming in one of the NCAR models. For the main reasons that, and overall there was like a direct, there's a regional warming that permeates in this region. There's a simple reason for this, that if you have smoke overlying a dark or bright, or a darker or brighter surface, you will either get a warming or a cooling of the climate, depending on whether more sunlight is absorbed in the atmosphere or more of it ends up getting scattered back to space. And it really matters on the details, how much is absorbed versus scattered, so the single scattering albedo, and then the reflectivity of the underlying surface, namely the cloud. So this was really a perfect problem for people interested in cloud boundary layer and aerosol problems. The sensitivity, this is taken from a simple, this is actually a pretty simple equation that relates the top of atmosphere forcing to the single scattering albedo and the cloud fraction, just to demonstrate where that trade-off happens between warming and cooling and climate. And the Southeast Atlantic was the perfect natural lab for this. There was, information we wanted that wasn't available from satellites. The models are under constraint. There's a lot of fires, primarily agricultural, and Southern Africa. It's about 1/3 of the global emissions in the globe. Large stratocumus subtropical deck there, one of the largest on the planet, and also a strong meteorological coupling that is bringing the aerosol into this large cloud event. So this is the type of landscape that we think gets burned. So it's a drier, grassier landscape than what Chris was showing. And for southern Florida, some organic carbon emissions are expected to be less than you would get for South Florida. But also, well, I'm described in the sense that, you know, they're agricultural, so this is a really nice paper, I think, that brings that out, that there's this weekly cycle to global fires, and not only that, that there's also associations with whether the region is either Christian or Muslim, and, you know, what their days off in the week are. Yeah. So, one of the first things we did was try to understand how this smoke could get transported so far off of the African continent, and this was work that my you know, ex-student Yemi Adedini did, where he ran a bunch of high split trajectories, which Chris also explained earlier this today. You know, just highlighted this kind of circulation that exists over the Southeast Atlantic that's also helps generate this cloud. So the reason why how we justified the field work out there was this was kind of our best guess at the aerosol cloud vertical structure in this region. And there's a key piece of missing information in there, which, if you were a class of my students, I would ask you what that was, but it's right in here, and, you know, this boundary between the aerosol and the cloud, that you don't really know how much is getting mixed down into the cloud field itself. So, yeah, so common objectives to all these campaigns were improve knowledge of the biomass breeding aerosol properties, get a better idea of the aerosol cloud vertical structure, and then understand how the cloud adjusts to the presence of the aerosol. There's several different ways in which this can happen. And, you know, ultimately, what one would want to come out of this is to do more ambitious modeling exercises that can take that knowledge and expand it to global climate modeling. So, so how does the smoke interact with the cloudy boundary layer? You know, questions one can ask is whether the interaction is mostly microphysical, so you have more smoke, more cloud condensation nuclei that give you smaller cloud drops that can either extend the coverage of the low clouds and, you know, by suppressing rain, or actually reduce it by encouraging evaporation, intermixing with the environment itself. Or, you know, there's different radiative interactions one might conjure up that depend on the aerosol cloud vertical structure. If there's more smoke in the boundary layer, well, wherever you have smoke, you're going to get absorption of the sunlight that will warm that local environment. And what that does for the cloud field, you know, depends on the vertical co-location with the clouds. So if it's in the boundary layer, the warming of the boundary layer will lower the relative humidity, and we would expect a lower cloud fraction as a result. But if the smoke is primarily in the pre-troposphere, so it's overlying the clouds, that primarily helps stabilize the lower troposphere so that you're trapping the lower level moisture and reinforcing the cloud field. So you really need, you know, these all trade off with each other. There's time scales involved with these. This microphysical time scale is fairly rapid, whereas radiation takes a little longer to come into effect. So you really kind of need to, measurements of all of these things, and then some pretty detailed process modeling to constrain these things, to elucidate these processes. So this is, what justified this deployment to the Ascension Islands, rather a very remote location. These were the things that we asked for, and there's a lot of overlap with this, and what Shanghai was showing for AMS-3. So some special things that we did feel we needed were the associated carbon mass concentration from SP2. Not that, I think the AMS-3 might have that also, so we did need to make sure that we had it for this. And well, a micropulse LiDAR to get the vertical structure, and then these cloud radars to get at the cloud presence. And I should add, because it's such a remote location, it was out there for 17 months, so it's really quite a project to keep this going. So the first thing we learned was that there's just much more smoke present in the boundary layer than we originally thought. There's really no evidence without going out there. The satellites couldn't see it in the boundary layer. They tend to get, the sea spray contribution tends to dominate what you see with satellites. These are from the 2 years. Yeah, there's, what is this, 5 months in there. There's a lot of interesting variability in this that we're actually still trying to understand a little better, but basically the pre-tropospheric winds are very strong later in like October and September, and that keeps the aerosol up in the pre-troposphere, and it doesn't mix into the boundary layer all that much. But in the first part of the season, the winds are fairly weak, and the fire emissions, when they come off of the continent, they go into the boundary layer pretty readily. So actually the cloud smoke interactions in the boundary layer are much more pronounced earlier in the season when the satellites had these things that more of the smoke was coming off of the African continent in September or October. And another thing we documented was very low single scattering albedos, which which we're still trying to understand where that comes from. But part of it is just that the fuel type that is very dry grass, so you get pretty relatively high light carbon emissions compared to the organic aerosol portions. But there's also an interesting seasonal evolution in this. So Jing Haosheng, his whole focus was on characterizing the aerosol cloud interactions. And we subdivided the days into smoky, non-smoky using the SP2 measurements. And this is just for August, when it's the month with the most smoke emissions, and saw a pretty pronounced decrease in the cloud fraction, especially during the day when you have the most absorption of sunlight compared to days without the smoke present. So this effect, it's been well known since there was what they call the Indo-X experiment. That was, I don't know, I think about 2000 or so. But this is the first time that this has been documented for this part of the world. And the interactions with the clouds are also a little bit different because it's over a warm ocean. There's it's a deeper cloud layer than you expect than you see in other parts of the world. So there's some decoupling of the cloud layer from the surface, and it takes, it's a slightly different interaction that hasn't seen in other parts of the world. And what was also interesting is, this black line here shows the seasonal cycle in cloud fraction in Southeast Pacific, where incidentally, DOE is also, there was also been a large fuel campaign out there compared to that over the Atlantic in the red. LTS stands for lower tropospheric stability. That's sort of first order control on the cloud fraction. And the different, the lower tropospheric stability is pretty similar between the two regions. Well, the seasonal cycle is similar. If magnitudes are a little different, but the behavior of the cloud fraction is different, and that's always, it had always puzzled me why that is, but you can actually explain this as an aerosol effect. In that early in the season, when the smoke is mixed into the boundary layer, it helps reduce the cloud fraction, whereas later on, when it's above the cloud deck, it helps to reinforce the cloud deck. So Amy Dubrocki is working on understanding the aerosol composition a bit better, and she visited BNL over the summer, so Chandra's neck of the woods, and worked with people there to do this analysis of the aerosol composition, and thought found something that we thought was pretty interesting, that so oracles is the aircraft campaign is a little bit closer to the continent, and when you compare the F-44, so this is a measure of the aging of the biomass aerosol, you can actually, even though it's fairly aged aerosol, you can actually still discern that there is the aerosol continues to age as it goes, between ages of say 4 to 7 days to say 7 to 10 days out by Ascension Island. And there may also even be a seasonal cycle in this, or so kind of a bigger question, I think, is so now we have data that's pretty well aged over in the Southeast Atlantic. There's a lot of data that's been collected near source to fiber emissions. We really kind of need more data that's kind of an intermediate to longer aged regime that possibly South Florida fire emissions could actually lend themselves very well to, because we have, they're frequent, they occur regularly, we can kind of control how we sample them a little better than we could for this far-flung field campaign. And a lot of this data is from the Western US, where anyway, South Florida just presents itself, I think, with some opportunities that have not been fully exploited yet, I think. So something that Amy is working on right now is that, there's a very nice relationship between the single scattering albedo and the organic aerosol, the black carbon ratio. And maybe fortuitously, the tropospheric values from the aircraft campaign line up well with that at least, meaning there's a nice linear correlation that fits both of them. It might be fortuitous because there is likely that there should be aqueous phase processing going on that would not be present in this. And we don't really know how, the relative attribution between oxidation processes and aqueous phase processing. And that's also, something that could be controlled better in South Florida. So this is, my last slide, just to, try to draw some parallel or make a connection between this, these campaigns over the Southeast Atlantic and what's been done over South Florida and what could be done in the future. And I guess I wanted to highlight this, paper from what year, I think this is 1967. But Sean Toomey was a huge leader in aerosol cloud interactions, kind of groundbreaking work. And his initial work started by looking at sugarcane fires in Australia. So it would be satisfying to kind of bring that to full circle here. So thank you.
All right, so our third speaker is going to be Dr. Marwa Alsing. So she's coming from Embry-Riddle Aeronautical University. So she'll be talking to us about the aqueous processing of the water-soluble organic compounds in the Eastern US.
Well, good afternoon, everyone. Thank you very much for the opportunity to talk today. It's such a pleasure to talk to folks in Florida. And it's been really want to do this for so long, to have air quality in Florida. Folks meet together to talk about what we can do for better air quality in the states. So today I'll be talking about increased processing of water-soluble organic compounds in the Eastern United States. And this work has not been done yet in Florida, but it's in the works. Pekita has mentioned at the end of the talk increased processing. So here it is. I'm going to be talking about that, in particular about the organics that are formed in the aqueous phase. So what are water-soluble organic particles? These are in short what we call them, and we refer to them as WSOCP. So for the rest of the talk, I'll be referring to those as WSOCP. And these can be either primary in nature or secondary. And while the rest of the morning was focused on the primary portion of aerosol, my talk will be focused on the secondary part of WSOCP. And in the absence of major biomass burning episodes, the WSOCP could be a good surrogate for secondary organic aerosol in most environments. This includes the absorbent, the aerosol that's formed through absorbent partitioning, and those that are formed through the aqueous processing. And if you're asking yourself, if you're in the audience and asking yourself, why are we interested in WSOCP? The reason is, it is a significant portion of the total organic compounds, if not PM2.5 in most environments. So how is WSOCP formed? It's basically when we have volatile organic compounds that are basically water soluble, and this is what we refer to as WSOCG, and they find the water droplet in the atmosphere, and through Henry's law, so at equilibrium, they partition into the aqueous phase. And for WSOCP, but this, once these compounds are in the aqueous phase, they can undergo reversible reactions or heterogeneous reactions, irreversible reactions. So the question of particle drying is very important because, as you know, relative humidity have a vibrational profile that they change across the day. So the question is, what happens to water-soluble organic compounds once the water evaporates? Are these particles going to remain in the content of that space because they were basically formed through irreversible processes? Are they going to revert back and repartition into the gaseous space because they were formed through reversible processes? And the question of whether these particles were formed through reversible or irreversible processes is critical because the magnitude of secondary organic aerosol can provide orders of magnitude depending on whether the formation is assumed to be reversible or irreversible. So this is really critical in the predictions of secondary organic aerosols using models. So the objective of this study is to characterize the seasonal formation of these particles, the water-soluble particles, in the Eastern United States. So we're going to look at the formation in different seasons. And to do that, we came up with a system that collects both water-soluble organics in the gaseous and the particle phases, and we measure them simultaneously. So basically, the water-soluble gases, they are collected through this chamber, and the organics are being detected using a total organic carbon analyzer. As for the particles, these are collected through a particle into liquid sampler, our pills, and detected with the same total organic carbon analyzer. And to characterize the reversibility or the effect of particle drying on these particles, our particle sample would alternate between two channels, an ambient channel and another channel where there's a silica gel dryer that maintains the relative humidity at about 35%. So the idea is to compare the concentrations between these two channels. If we don't see any change, that means that there's no effect of drying on the particle concentrations. If we do see an effect, that means some of these particles have evaporated back into the gaseous phase. So the sampling location took place in Baltimore. This study was in Baltimore. And all that system that you just saw was placed inside an environmental enclosure that placed on one of the engineering buildings on their campus. Just for information, we have a similar setup now at Embry-Riddle for purposes to have a system like this on our campus. And the idea here is to start sampling what starts from 2014, and then we sample for about 2 months each season. In particular, for the spring period, we have to divide this into periods early and late spring because we have seen a different behavior of or effect of particle drying on these particles, as I'll show you in a little bit. So here's what we're going to do. We're going to collect water-soluble organic particles. We've done that. And now we need to analyze it to detect what's happening as a result of particle drying. So this is our secondary water-soluble organics. This is made of two portions, like I mentioned, the absorptive as well as the aqueous. The AQ-SOA, that is the secondary organic aerosol that's formed from aqueous processes, would be identified when based on a relationship between the partitioning coefficient, or FP, which is basically the ratio of particles to the total gases of particles, versus relative humidity. If we see a statistically significant increase in FP as relative humidity increase, that would infer formation through aqueous processes. And once we detect that aqueous S wave, then we can look at the reversibility of that formation depending on the ratio between the dry to ambient WSOCP. If the ratio is too close to unity, that it will indicate irreversible formation, whereas if the dry to ambient concentrations are lower than unity, that would mean that at least some of these particles were formed through reversible processes, so partial reversibility. So let's see what's happened in all these seasons, investigated seasons. So this one here, the partitioning coefficient as a function of relative humidity during the nighttime, because fortunately we didn't see any formation during the day. And I'll explain that in a minute. But we can see that for all these seasons, for the fall, the winter, the late spring, and summer, we did observe a statistically significant increase in the partitioning coefficient as relative humidities increase. And just to note that each of these markers are at least 100 data points. So what this is telling us is that there is evidence of formation of aqueous formation of WSOCP during all these seasons during the night. And this has also been observed in other parts of the Eastern United States. So Atlanta has, there's evidence of aqueous secondary organic aerosol at that location. And that would be the case in many other parts in the southeastern United States as well. So why do we not see formation, aqueous formation of WSOCP during the day? This warrants looking back at are these particles formed. These particles require aerosol liquid water. So let's look at the climatology of aerosol liquid water in Baltimore. This is based on 5-year averages, and we segregated the data into daytime and nighttime. And for this analysis, we're looking at inorganic water. So we're modeling inorganic water using isotropia model. We're calculating organic concentrations of organics as well as some of the physical properties of these particles. And when we sum these two up, inorganic and organic water, come up with the aerosol liquid water, the total aerosol liquid water. So what we're seeing here, that during the daytime, for all of the seasons, concentrations are too low of aerosol liquid water. There isn't enough water for WSOCP to form in the aqueous phase. Whereas things are completely changing during the night. Especially during the late spring, summer, and fall, there is sufficient water for aqueous processing to occur. And that's why we did not see any formation during the day of aqueous secondary organic aerosol or aqueous WSOCP. So let's go back to the question, the main question that we wanted to address. How is the formation of AQS wave? Is it through reversible or irreversible process? And to address this question, let's look at the ratio of WSOCP dry to the ambient in the different seasons. And again, if it's unity, it's reversible, irreversible. If it's deviating from unity, that's reversible formation or partial reversible formation. But note that we'll start with the early spring because we didn't observe any AQS formation at all during that time. And that was because the aerosol liquid water, even at night, was not sufficient for that formation to occur. But we did observe AQS formation in the winter and in the fall. But still, the ratios of dry to ambient are still too close to unity. That infers, or that means that the formation is basically irreversible in these two seasons. But that's not what we're observing in the late spring and the summer. Now, these ratios are deviating from mean, indicating that we have evidence for reversibility during the warm seasons. So in a nutshell, in the warm seasons, there's evidence of reversibility, while in the cold seasons, there's only the west way is poured through air processes. So why? Why there's difference between warm and cold seasons? So let me show you. I'll bring back isoprene. Talk slightly about this. So the region is well known for high isoprene emissions during the warm seasons, during the ozone season. This is climatology of isoprene concentrations for the last 10 years in Baltimore. And as you can see, concentrations of isoprene are minimal in the cold seasons. And as they start increasing, get into our late spring, early May, which is represents our early spring season. And they continue to increase during the ozone season, and then in September, they go back down again. That's our fall season. Well, yeah, identified as our fall season. So in a way, isoprene trends are really capturing the trends in our reversible AQS wave, irreversible AQS wave when in cold seasons, and then as isoprene concentrations increase, we see some evidence for reversibility. This, together with time lag analyses that I'm not going to get into this afternoon for the sake of time, but I'd be happy to talk about it offline, and if you're interested also, you can check out our paper in ACP in 2018. These time lag analyses, they show that there is a relationship between isoprene and the evaporated mass after 9 hours. So after we measure isoprene concentrations by 9 hours, and we look at concentrations of evaporated mass, there is a link between the two. And it's not just isoprene, it's also NOx to isoprene ratios. So really the interactions between biogenic and anthropogenic emissions are crucial in the amount of evaporated mass that we see during the warm seasons. But what's happening in the cold season? Why is it irreversible during the cold season? In the winter, things were very interesting because let's look at air-soluble water during the winter in Baltimore. This here shows the concentrations of air-soluble water. Again, total air-soluble water, both inorganic and organic, as a function of temperature. And as temperatures increase, the concentration of air-soluble water increases. This is great, right? But we only observed AQS wave formation in the winter between 0 degrees and 10 degrees. So why are we not observing AQS wave formation at higher temperatures than 10 degrees if the formation was only dependent on air-soluble water? It makes sense that if it was only dependent on air-soluble water, you would still see the formation of that aqueous organics at higher temperatures. But what's interesting here is that the formation wasn't only dependent on air-soluble water. In fact, it was also dependent on biomass burning. So when we put potassium concentration, which is a precursor for biomass burning, now we get a better understanding of what's happening. The story here makes more sense. The concentrations of biomass burning were decreasing as temperatures increased during winter. And the only time range where there was sufficient amounts of air-soluble water and sufficient amounts of biomass burning precursors was in 0 to 10 degrees Celsius. In that temperature range, the range that we did observe aqueous WSCP formation. That means in the winter, the formation of these particles is dependent on both the amount of air soluble water as well as biomass burning as well. So in conclusion, I would like to conclude by some remarks that we did observe the secondary formation of WSCP in the aqueous phase in all systems. This phenomena is important throughout the year in the eastern United States. And we anticipate that this will even be of higher importance here in Florida. Relative humidities, when we compare relative humidities here in Baltimore, definitely they're higher. So there is abundance of air soluble water in this region. We did not see an effect of drying during the cold seasons. We did see evaporation of these particles, so evidence of reversibility during the warm seasons because of biogenic emissions, basically isoprene. And during the winter, the formation, the aqueous formation is dependent on biomass burning as well as air soluble water. So this work has several implications. So from the atmospheric chemistry point of view, from the atmospheric modeling, in closing the gap between the secondary organic aerosol measured and the model. And also it has important implications for the methods such as the federal reference and federal equivalent methods that monitor PM 2.5 in all the network, the stations across the US. These methods for measuring PM 2.5, they rely on particle price. So are these stations prone to any biases because of that amount of mass that we're not capturing as we write particles? That's a big question mark. In fact, as a result of this work, we did see a bias that goes up to 25% in some instances. So I just want to end this talk by some of the ongoing work in our research group. So we are continuing to address this question of evaporation of AQSWA and WSCP. And as a matter of fact, we did observe that this evaporation is function of different parameters, meteorological and environmental, including relative humidity, including the amount of pre-existing water-soluble organics in the atmosphere, including isoprene and NOx to isoprene ratios. And we're currently working on coming up with a model, a machine, we actually did come up with a machine learning random forest model to predict this amount of evaporated mass. And we're implementing that in different areas in the eastern United States to predict how much that evaporation could be in this region, in different parts of this region. Also, in the work that we do, aside from that project from Aqueous Processing, we're looking at some environmental justice, and we're calling it the breathing infrastructure. We're looking not just on air quality, and we're not only interested in air quality, but the interactions of air quality with people's perception to air quality and also emissions from traffic. And this is our sustainability really kind of application of that work. We mentioned drones, and there's a lot of work about drones. So I come from Embry-Riddle Aeronautical University. As an aeronautical university, we have a fleet of drones lying around in every corner. And that prompted really the use of those in an air quality perspective. So we're using low-cost sensors to fly on drones and integrate them on drones. And we currently have an EPA P3 project working on that. Finally, last but not least, microplastics are becoming very important components in the atmosphere, and there's a lot of attention about those particles. It's not just what we're measuring in the stations by the EPA might not just be organics or inorganic material, it could be any particles, any aerosol, including microplastics. So we need ways to better characterize microplastics in the atmosphere, and I encourage folks from the instrumentation to really think of ways of looking at microplastics and characterizing them and working with us to detect those toxic particles. By that, I would like to thank the funding agencies, my collaborators, and the students for working on all these projects. I'd like to thank you all for your attention, and I would love to have any of your questions in panel discussion. Thank you all.
So can the speakers get seated on the stage? So we're gonna have a panel discussion. Okay, any questions from the audience? Yep.
I have a question for Marwa. So I think very interesting talk. So is it possible to coupling your results in the existing models for some like climate change or some projection?
I would love to do that, and I would like to collaborate with someone to do that, like CMAC, and see what were the implications, how the models would change. And that's why we're working on that machine learning model for these predictions so that we can implement them in those models.
So will they kind of influence the radioactive forcing? Will it influence that?
That would require more measurements in different locations. So more field campaigns, and that's why we're conducting these measurements in Florida, so that we can add more data points and get more robust results.
Okay, maybe I'll ask one general question to all the presenters. So, I mean, since our session has a title, has the word of instrumentation, right? And we have the instrumentation companies also joining us. So what do you think is the limitation in your deployment or to answer your scientific questions? Let's say, if you can imagine an instrument, a perfect instrument that can work really well for your study, what's that going to be? Just one. It doesn't have to be a wish list. Just one. Most present. Yeah, most present instrument.
My current soapbox is I don't like to use the term low-cost sensor because of what it implies. And I'm sure if Rick Lagan were here, he would have some thoughts too. But you know, ARM operates instruments 24/7, 365 days of the year, and they're manned by they're managed by operators who don't necessarily have a background in aerosol sensing technology, and we can't have a PhD operating instruments 24/7 sometimes, right? So just generally, instruments that don't require a PhD, right? That's a general comment. The second one is transparent uncertainty quantification. Now, I know that gets in a little bit of secret sauce for some companies, but for us, it's critically important understanding what are the real limitations and propagating that air, especially for molecules. So we're not competitors, right? We're scientists. Just help us better understand what are the real uncertainties, what are the real challenges of measuring. And then the third one is another general. Sorry. Data availability. Most of the times, that's not an issue, because you buy the instrument, you make the measurement, you own the data. But now that there are these lower complexity instruments, where part of the value is that you don't have to manage the data infrastructure. It sits on a cloud somewhere, right? And for most users, that's good, because you don't want data accessibility to be burdened to extract meaningful scientific information, like the purple nanosensors stuff, you know, the kind of PM sensors. But if you want to do any type of research level work with it, you need access to the raw data and whatever transformations are being done. And yeah, that last one is a current challenge for me in trying to develop a sensor network with what's commercially available, is who owns the data, right? And if I could specify an instrument, right, that would be, having instruments that are kind of robust for mobile platforms. So I think that's always been a general desire. And from just a personal exposure, right? Like, I'm not an exposure scientist, but I recognize the value for having something that you can have with you. When you're cooking, when you're mowing the lawn, things that can give you some indication about what your actual exposures are to trace gases, aerosol.
I would also add, having a platform for all these devices where you can integrate the data into one platform. When you're using a lot of equipment in a field campaign, they're not, time is not aligned. I'm working on data from SOAS in 2013, and it's just it's the same campaign, and finding the time to be aligned together to make a meaningful analysis is just a pain. So I think a better way to place, and I guess it's with who owns the data, accessibility, that goes back to that point. So I hear you on that.
It's one of those things where the rubber really hits the road, not really when you're doing the deployment. After it's done, you gotta work up all the data, do all the QA/QC, and that takes so much time. And shout out to ARM, credit to ARM, they try to offload a lot of that. But there's still a lot of stuff needs to be done. It's still an effort and a project and a lift, right? Just to even get to the fun stuff about discovery and learning something. And I can't tell you how many times where I had to go explain that there were these issues with the instrument that somehow didn't get aligned with the data stream. And so anything that could lower the burden for QA/QC and understanding the usability of the data lowers the burden for entry for everyone to work with data that comes, right? A lot of the vendors that are represented here. It's a big ask, I get it. We're all overworked, right? But coming up with, an approach to make that easier.
This is becoming very important in a time when we are in an era of big data. And with the machine learning and models, we do have a lot of data to analyze and to look at and to make meaningful conclusions using that data. So we need to have data sets that are easy to use.
Okay.
Thanks all three of you for saying really great and inspiring thoughts. I have a question for Marwa. I was pretty curious if you could think a little bit more about the microplastic work that you have going on in your lab, and if you can tell us anything about whether you're looking at microplastics in Florida, I'm really curious to know more about what your program is there.
Sure. So I started this work when I was doing my postdoc in CSU. And the National Park Service folks, they are so interested in microplastics because there's evidence of microplastics in remote areas and snow. And there's no way for that snow to, for these microplastics to be transported to make it to these locations except through transport in the atmosphere. So at that time, I came up with, there was only 1 or 2 studies at the time who looked at microplastics in Paris. And we came up with a sampling, active and passive sampling for measuring the deposition as well as the concentration of these particles. So after I moved to Florida, that was the first project that I actually acquired in the lab. And I started sampling on campus. So we do have samples and evidence of microplastics in Daytona Beach and also in Baltimore on Johns Hopkins campus. So we're collaborating with Johns Hopkins to look at the human health impacts of microplastics. As a matter of fact, we're writing an NIH proposal about that these days. So it is there. And it's there for different, it is in the atmosphere, these particles, and they range in size and in composition. So we look at them through the microscope for size distributions. And we came up with a pretreatment a methodology, and that's the paper in preparation right now. So we can eliminate all of the other organics in our samples, and we're only looking and capturing our analyses are only for these particles. And then we confirm what we see in the microscope through chemical characterization.
I was curious, can you, just a quick follow-up question, can you look at filter archives to look for
Yes, I can.
evidence? You can see where I'm going with this.
Yes. Yes, I'd be interested in doing that.
Yeah, Chunko, you mentioned, coarse bone aerosol being sort of the Wild West. I kind of put microplastics right up there, if not a little higher. It's so much we don't know about the microplastics in the atmosphere.
That's correct, and especially that there are a lot of papers right now talking about microplastics in the atmosphere, but they're focused mainly in China and in Europe. There's very limited studies. I mean, there's a paper that came out in a couple of years ago in Science. It's called plastic rain. So we're not just looking at acid rain now. We are in the era of plastic rain. I mean, I really recommend that you read it. It's been a very interesting paper, and it's a national prize, but it's all in the Western United States. So you need to make measurements in different locations. And there's evidence that the microplastics in the water, they make it to our air. And now that we are in coastal areas here in Florida, we're definitely that source of marine microplastics in the atmosphere is intriguing.
Well, I can't wait to read the report when it comes out. So thanks for sharing that.
Yeah, listen.
Chiang-Kai, this is a question for you. What would be the desired features for the network since you are talking?
Yeah, thank you for asking that. So for the systems that I am proposing for the NF3, a week of continuous operation, unattended. So it's not crazy, like a year, but a week of unattended operation, solar power would be great. And of course, feel bad for harping on data, having some backend solution for data collection and integration and flexibility. You know, for Department of Energy, I would prioritize the measurement categories. Highest priority, I would say, challenge me on this one, I'm just kidding, no. Size distribution, right? Let's do size distribution from the nucleation load enforcement. Right. Some chemical composition, whether that's offline or online, right? Some information on hygroscopicity, whether that's subsaturated or supersaturated, right? Black carbon. So like fourish, those have fourish measurement categories. The highest priority would be 10 nanometers to 10 microns, just as an approximate size range. I recognize that covers maybe 3 different instruments. I recognize that, right? And I also recognize that there should be trade-offs because you can't, if you could have done it for 5K, it would have done, I think. So I recognize there are trade-offs and I'm willing to make them in areas such as maybe time resolution, size resolution. Because if what we're trying to capture is spatial extent, then we don't need something like an ALS, which is designed for micro physical study, process-based study. If spatial extent is what's the driver, then yeah, we can give up resolution, we can give up time resolution. But getting again to the operational burden, right? It's a week in Northern Alabama environmental conditions.
I'm sure you're aware of the sale being pursued, right? We have more network, 6 stations. In each station we have a part, which measures size distribution from 130 nanometers to 30 microns. We have a mini C-scanning company. And we also have sample, we have some time result sample, collect samples for offline research. And for our purpose, for the current project, we are just trying to analyze iron component, sample for offline. So in collaboration with this. Do you think this sort of network will be of value to you in the thought?
Yes.
And we have been running this for 1.5 years. So most of it continues, especially the part that they continue. The system, mini system kind of has from time to time in code types it got broken. But I think in southeast the chance of getting broken way less than in the mountains of Colorado.
Okay, my question is for Dr. Zulema. You mentioned about that cloud fractions are often reduced when smoke was in the boundary limit. Could you comment if the smoke is fresh or aged? Like how does that influence the cloud fraction?
So the question is, when smoke is in the boundary layer, the cloud fraction decreases. And does that depend on if the smoke is fresh or aged?
Yes.
It depends on the ability of the smoke to absorb something. So as smoke ages, it goes through this process where the single scattering albedo tends to increase in the first day or so as more gases and small particles coagulate on it. And then that material goes away, however, through various processes. And the single scattering albedo will lower again, so more sunlight is absorbed. So when the smoke is highly aged, I would expect that cloud response to be more pronounced. So one interesting question I think out there is, there's this idea that as smoke ages, it all starts to look alike. And I guess, I'm not sure if the verdict is out on whether or not that's really the case, but that would be kind of interesting to know also in regard to that.
I have a question. So you talked about black carbon. How about brown carbon? How do you see brown carbon emitted from smoke and secondary organic aerosols, especially with the aging?
That's okay. Question was brown carbon. We don't think there's much brown carbon. So that's why I didn't really mention. Probably less than 10% of the overall absorption at short wavelengths. That is probably different over Florida, where there's more material. Any other questions? I have a question for Shanghai. Oh, yeah, that's a good idea.
Yeah, Pakita, do you want to ask your question?
Yeah, this is for Shanghai. You know, the daydreaming, like, so you have this wonderful facility in North Alabama. And how it would be great to find, build science on it that extends down to Florida. So it's kind of daydreaming how people would do that. That's kind of cheap, maybe just things that can be attributed to existing work. And one thought I had was it would be nice to know the high split trajectories that emanate from the AMF tree, and just see which ones go to South Florida or come up from here to your station. And that seems like something that could be easily done by arm, like just have this spot where they're just kind of accumulating 4 times daily high split trajectories. I was wondering if that idea has come up, or what do you think? And, yeah, respond to any part.
Is there anyone from ARM here besides me? Okay, good, and I feel comfortable speaking for ARM. I think ARM should be doing that because it's their operational philosophy to support the interpretation and understanding of things like air mass trajectory. Now, I've asked them if we could operationalize that for AMF3. I think the pushback is that let's test it out on an island basis first, which I'm fine doing. So I am more than happy to help push that idea along, especially during the planned intensives for AMF3. And I really like how you're daydreaming, because whenever I get questions about what about Florida, and I have, my answers are when the DOE aircraft becomes operational, when it becomes operational, let's propose a campaign that does transects between AMF3 and a site where you're getting flow off the Gulf that eventually passes into the Northern Alabama domain or vice versa. And do things like, hey, we're maybe in enough of the same land surface environment that there's similar coupling. but the convection's different enough that you can do interesting contrast studies. Now, it's almost like doing 2 AML campaigns, so the scope gets big, but the questions are really interesting. And my second answer is ARM is. This is another question for you. How many are familiar with the urban IFL projects that DOE is funding? These urban integrated field laboratories. Okay, so ARM is looking into deploying smaller measurement nodes to help capture gradients and transitions. So maybe something that can speak to lower resolution, coarser type of measurements, where that trade-off is good because what you're getting is transition to gradients. And, that's something that once ILP season rolls around for AMF3, I would think it'd be interesting to propose something that doesn't transect from coastal environment to an interior environment. And now, but this is me daydreaming now, right? And, in my role as a PI, I will help out in any way that I can to grow the deployment landscape and ecosystem. Were there other parts that I missed?
No, that was good. Yeah.
Okay.
Okay, so do anyone online have any questions? Okay, so now let's give responses. So maybe we can conclude our session, and then we're gonna have a half-an-hour coffee break here. So enjoy some coffee and nice conversations. We'll be back at 4:30 for the tutorial that's given by Dr. Pratim Biswas. Okay, all right, let's back out. Yeah.
There's a lot of, it is a strongly forced system sometimes. And then sometimes it's just first stagnant. It's just good.
Okay, thanks, Yang. Let's get started. This session is more for the students. So the sort of senior investigators can take a nap or grab a coffee. But students, no taking a nap. I'll call you and ask you a question maybe or two. So this being the first workshop, we felt that we'll have a mix of tutorials and of course you heard some fabulous sessions, and we also want to gear it to students. We are also going to have a survey later. Maybe the tutorial should come up front so some of the students could get the material, basic stuff and be ready. And so please provide feedback when we send that out to you. And I'm really going to keep this very basic. And of course, I have 40 minutes, so I can't cover everything that is listed there. But let's see, I'm going to start with what is an aerosol. So please pardon me, all the experts here, or maybe check my definitions. There are three things I'll talk about. One is characterization. We are going to have instrument demonstrations, so maybe at least that topic relates. Particles move around, And then there's dynamic processes associated with particles. We already heard about new particle formation, fresh formation, growth. So I'm very quickly going to go through this materials. Of course, they rely on standard textbooks. Most of you might know all these books, but students, again, always good to have a book. And there are many other books too. We also have some fabulous lecture notes. My entire class, by the way, I taught this aerosol class for 35 years in a row. Coming here, I get a break now, but we put it online. So if you want a series of lectures on basics of aerosols, feel free to access this site. And it's pretty good. It's on a smart board kind of thing. And then Yang Wang is here. When he was a student, we solved a lot of problems, mainly through our classes that we taught. We compiled these. So if you want to work on some interesting problems, the last compilation is also very nice. So let me tell you this. I don't need to say that, but if I go outside this room, catch a student, ask them what an aerosol is, they'll think it's something coming out of a spray can. It's, of course, we all know a lot more, you heard it. But I always like to call particles the good, the bad, the ugly. We might have heard more about the bad ones today, maybe some good, maybe some ugly, right? So it's very broad, and oftentimes that good part gets missed. Tomorrow we are going to have several industry folks. There's an entire session on nanoparticle technology. So using these same principles, there are a whole bunch of engineered systems that are run to actually produce these particles, right? And then they're, of course, put to use. And there are many fascinating applications. If you want to look at next generation solar cells, if you want to look at advanced materials for catalysis, we heard in the morning, I think I saw a slide that there are some catalysts coming out with the dust and so forth. You know, you actually make the catalyst by these gas phase processes. So it helps also to tackle global challenge problems. I come from an engineering background, so I want to overcome some of these problems. And we use particles to overcome these. So I'm going to just walk you through. If you really look at it, we start from a molecular state, right? There are small molecules. There could be molecules of different kinds. So we just give it the name multi-species. As you go along, they begin to cluster together. And this is what we really run in a laboratory reactor too. It could be the same that happens in the atmosphere and so forth. So the basics are applied to many different systems. And these clusters could be multi-component, right? And I want to design these particles, or I want to understand how these are coming together. If it's the atmosphere, I don't control, I'm just going to have a clean system. Clearly, one species might dominate, but I have many other species. And same way in the laboratory or an engineered particle, I want to intentionally design it so that I can tune the ultimate properties. And then there are collisional growth mechanisms. These things have a mind of their own. They move around and they can collide. Some of the molecules then see a surface and directly condense. And all of these processes make the particles grow. So they become larger in size, as you can tell. And then, of course, I'm interested even downstream. If it is an engineered system, I want to collect it. If it is something in the atmosphere, I want to know how they move about. And we heard some fascinating examples. And just by tuning these things, I can get different shapes, different compositions, and all of this are put to many, many different uses. So just to give you, we heard a lot about climate and environment. We heard a little about health. We'll hear more about health tomorrow. Advanced materials, you'll hear maybe in the last session. And even making drugs, right? I want to make a pharmaceutical drug. I want to deliver it, right? If I want to treat asthma, what better way to treat it than to make an aerosolized pharmaceutical compound, right? Energy, I just mentioned. Agriculture is another one. We don't realize it. You deploy large volumes of pesticides, and we of course dump a lot of fertilizers. Most of it runs off. You know, the plant is very picky, but the farmers want these crops to grow very rapidly. If I instead use the foliar method of delivering nutrients, I could be very efficient. And this is smart agriculture, it's precision agriculture. So aerosol science is being put to good use there too. And of course, a whole bunch of commodity powders. I'm not going to give any research presentation here, but we really work on all of this in different ways. Today, it's going to be very basic stuff. This is where you can now go take your nap, the senior folks. Students, please be alert. Particles are characterized by a size, right? What do I mean by size? Of course, the simplest one is the diameter, right? But of course, a diameter is associated with a certain shape. So we got to keep that in mind. I also want to know how much of these particles. So are there any other metrics? Why should it be only a linear dimension? If it's a catalyst, if it's a photovoltaic device, could it be the surface area, right? Could it be even the mass or the volume? And of course, we use these different metrics, but more often than not, the diameter is the common metric. If the shape is defined, I can convert one to the other. So we keep all of that in mind. Then I come to concentration. Same way, I can sit and count my particles. I have a number concentration. I take the mass of these particles. It's a mass concentration. And I don't stop there. I could have different moments of the size distribution to represent concentration, right? And just to look at it, we are in an indoor environment. I see some folks wearing masks. Depends what kind of particles we are trying to avoid inhaling, but concentrations typically would be 10 to the 3 particles number per centimeter cube, right? So even in a small centimeter cube, there are 1,000 particles floating around. If there are a lot of people here, it could be an order of magnitude higher. If I start burning things, I think the TSI folks are going to start cooking at the back in the next session. They're going to reach much higher concentrations. If they're truly cooking, that is going to turn on a heating element and so forth, right? We are very familiar with the mass concentration because most of our regulatory dictates are based on mass concentration. There's no regulation as far as I know based on number concentration as yet. So we know PM 2.5, we know PM 10 and so forth, okay? So let's continue. The size distribution function is an important parameter. It's used to characterize polydispersed aerosols with a continuous distribution. And I can have some functional form, n as a function of dp. How do I define little n? It is just the number divided by the size interval. If I'm using diameter as that, if it's a continuous function, I can take it as a derivative. In the same way, I can define volume as a metric and have a volumetric size distribution. And for spherical particles, the two would be related and so forth. Okay, so the size distribution function, next session, PSI folks might be presenting to us a size distribution function, which they actually measure. But very important is that this is related to this number concentration. And of course, time is limited here. They gave me 40 minutes, so I'm going to cram a lot of things in, keep track of time. So best thing is to just pick an example and not even follow all the numbers. So you look at the size interval, and I know how many particles there are in this size interval. And I can have different size intervals. Obviously, this might come from an instrument, right? We need to know how this comes about, or some kind of data that we produce. I can write a cumulative number concentration, I can look at the size distribution function as I defined it. And then here, as I said, I have about 12 bins. How do I represent this graphically? Numbers are great, but we always like to see this in the form of a graph, right? How do I plot a graph? Again, very simple things, but just to illustrate, I could do it in a number of different ways. So here, I'm just plotting the number of particles in each bin, right? The bin is of course given as a histogram, and I can plot the number concentration as a function of the diameter, and it looks something like this. Okay, now the next one, as I defined this, the size distribution function, I can take the number concentration in each bin and divide by the width of the bin. And you see that the graph begins to look very different, right? So depending on how we plot this, I have different shapes, and the visual, a first quick visual look tells us many different things and sets up different impressions. But I want to be as holistic as possible by looking at this. So is this the best way to do it? Is it representing the entire distribution that I had in a tabular form? So instead of that, here now again, I'm plotting this delta n by delta dp, but the diameter on a log scale. So you just see that even changing the scale, of course, this begins to become more prominent now. Before it was all squished. We also heard there are many orders of magnitude of the particle diameter. So you begin to maybe get a better picture, right? Now, is this the best? Right, I'm going to say that probably the best way to do it is to take delta n and divide by delta log dp, not just delta dp. And you see now the modes begin to show up in the distribution, something that we never captured in those previous graphs. And of course, the diameter or log of dp on the x-axis. So simple things like this. Now, depending on what you're interested in, you might make different plots. But pretty much we come up with certain conventions, let's always plot delta n by delta log dp. I think Chong Kai was saying, how do I get all the data together? Of course, he was talking of just collecting the data, but how do you also visualize the data? So these things are important, simple things. Okay, now I can define a bin size. How do I define this bin size? Do I take the mean value? Do I do something else? That's another parameter, because ultimately I might want to get that continuous distribution so I can fit an equation and then play with the equation in other things that I want to do. So the choice of diameter to represent the bin size, right? In some sense, it's arbitrary. I can, of course, take a mean. I can take a geometric mean. I can do all kinds of things. So this just shows us that using different things, there's a little difference in this distribution. So I can know how to convert a histogram to a continuous distribution. Why do I want to do it? That will become very obvious. And you also heard in the morning, if we want to run models, we want to run write up equations, it's always good to have sort of formulaic representation. There are certain shapes which fit the distributions very well. Right, so these are now very compact form. So let's look at the normal distribution. Things look very normally distributed, Gaussian, but this is very problematic. For example, I put a negative size in to a Gaussian expression and I get a positive number concentration. Obviously, physically, there's no negative size of a diameter. So it should be 0 at best, or it should say something to me. But here I end up with a number. So obviously, this is problematic to represent size distributions. Again, using a log scale allows me to mathematically constrain it. So when I use log of dp, there's no way that I can put a negative number. The log function is not even defined for that. So it sort of constrains it. And all of this, again, simple concepts. But when I start running complex models, writing pages of code, these all become very important. And every check and balance that is put in an automatic manner is extremely good. And this also matches the shape that we measure in the atmosphere. There's a tail. If you look at it, there's a certain tail in the distribution and so forth. So the size distribution function is a function of the diameter, is a function of the geometric standard deviation, and it is a function of the geometric mean size. So there are two parameters, of course, the total number concentration, the geometric standard deviation, and the geometric mean size. Okay, so these can then define the distribution. Is it all encompassing? Definitely not. But in many practical cases, I can fit something like this and use it. Okay, then once I have a mathematical form, I can do all these mathematical manipulations, very simple things. I integrate from 0 to a certain size dp. I divide by the total number. This gives me the fraction of particles up to a certain size dp, right? And that's important. I'm sitting and inhaling stuff. I might want to know only the total stuff that I'm inhaling up to a certain size, and having a compact expression like this, relating it to the geometric mean size, geometric standard deviation, allows us to calculate these things readily. Of course, they start getting more and more complex. And how do we interpret such derived expressions? For example, if this were a mass distribution, I could set my capital dP to 2.5, and this is nothing but the definition of PM 2.5, PM 10, PM 1, PM 0.1. So allows me to very quickly play with these things. Then there are moments of the size distribution. It's not just integral properties. We heard about light scattering, single scattering albedo, right? Maybe the sixth moment of the distribution might give me a good idea of the scattering albedo of an aerosol, right? So I might want to define the sixth moment accordingly. If I have a certain health impact, I might define it. And very interestingly, mathematically, the kth moment is related to the 0th moment, which is nothing but the number concentration, and by this simple expression. So having one moment and the parameter, I can then calculate any kth moment. Again, all of this done very compactly. Okay, and I'm not going to go through this. You can then look at different types of distribution, the number distribution, surface area distribution, mass distribution. The key thing, again, visually, you see which sizes dominate, right? So the number might be dominated by the small sizes. Again, some of these are obvious, but quantitatively and visually, it's good to look at that. Not everything is spherical. This is my only slide about non-spherical particles. In fact, most of the particles we encounter might be non-spherical. I might use a fractal concept. It's just a geometrical concept which allows me to define a shape of this agglomerate or aggregate. Many times particles come in aggregate form, especially from a combustion system, especially that's floating outside, or in a aerosol reactor when I make stuff. I want to know the shape because this might be a good catalyst, but may not be a good photovoltaic material or some other material. And there are again mathematical expressions. And then I have additional parameters, in this case, the fractal dimension to determine, right? And of course, we know by this geometric expression, if the fractal dimension is close to 3, it's close to spherical. So in addition to representation, it also gives us some idea of the shape. Okay, again, one slide on chemical characterization. You heard a lot about it. I really want to know the size-dependent chemical composition. When someone asks in the previous session, what's your dream instrument? I want to know everything about the particles, which is the size distribution, but I also want to know the chemical composition at every size, right? I can have an elemental composition. We tend to do that a lot when we do source apportionment. You of course heard about organic species. Typically we do averaging and so forth. And these of course are related to all of this. If I'm making a useful material, extremely important what composition. It's not just the elemental composition, it might be the crystal structure, and these are all also important for health effects and things like that. So we can get into a lot of detail when we deal with this. My only slide on biological aerosols, right? Different shapes. It could be bacteria, viruses. It could be a DNA fragment. It could be a protein fragment. And many times I want to measure these. I think Naresh is here. He'll talk about pollen tomorrow, maybe. There are protein fragments in pollen which cause the health impacts. It might not be the entire pollen particle. It explodes. Some of these are dangerous sounding. We of course know about the SARS-CoV-2 virus and different sizes, different shapes, and different impact. So biological aerosols are also very important. Okay, so finished size distribution. I have to quickly finish up these other topics. So let's move on. Particles now move, right? If I have a particle here, an aerosol, it's going to move. Why is it going to move? Because it is going to interact with the gaseous molecules. As long as I'm not at 0 degrees Kelvin, we know from the kinetic theory of gases, my molecules are moving, they're colliding with the particle and imparting a motion. Then of course, I might have a flow, I might have a fan that is working and push these things off. I can't talk about all of these. I might not be too happy about the movement in some sense naturally, or maybe in a flow system. I might want additional forces to be imparted. We do this in the exit of a combustion system. We want to collect particles, we charge them, we trap them in an electrical field. So all these fundamentals of aerosol transport are very important. So again, repeating what are the questions to answer. I'm not going to talk about everything. There are some fundamental properties. I also need to know about the gas, the mean free path. It's the distance a molecule moves. It's that scaling which is so important. That's of course related to the speed of the molecule. The average distance a molecule moves before it collides with another is defined as the mean free path. I can get an expression. Again, just go through these very rapidly. And depending on this mean free path, I get different size regimes. And very interestingly, depending on the size regime, which is based on this non-dimensional number, the Knudsen number, I have different transport properties. I have different properties of these particles that we have to deal with. So the transport characteristics depend on this size regime, where I fall in, right? So if there's an instrument that's measuring in this size range compared to this size range, I have to, of course, design algorithms to invert the data with the appropriate relationship. Again, very quickly, I'm not going to go through all of this. So who recognizes this gentleman? You know, I was talking to Joe earlier in the day. We really need to have our students learn the history of our field, right? But of course, we like to call everyone an aerosol scientist. So this example holds for this. So this is Isaac Newton. He, by the way, came up with expressions for the drag force on a particle. So whenever a particle is moving, at least in an atmosphere, it's going to experience a retarding force, right? There's a lot of derivations. I'm not going to go through this. Let's now just jump into formula. By observing things like even planetary motion, like things moving around, he could calculate things like the drag force completely empirically, way back in 1680. So we label him as one of the initial aerosol scientists. This drag expression, very surprisingly, with this coefficient holds even today. Of course, Stokes came by, Cunningham came by, all kinds of regimes, Boltzmann's calculations, and by just using the appropriate definition for this drag coefficient, as we call it, as a function of the Reynolds number, I still have a valid expression that we use. So we recognize that and we can use it. Of course, there's a lot of details one could go into. Simple calculation, right? I take a particle, I leave it here, there's gravity acting. So there's a gravitational force, by the way, we attribute that to Newton too. As the particle settles, there's a drag force. We go back to, the BC era, as was called. There's a buoyancy force that Archimedes came up with. And I write an equation and I can solve this equation and get an expression for the settling velocity of the particle. So very simple concepts now being brought together. It's a function of time. Very rapidly, it reaches a constant value, which we call the terminal settling velocity. It depends on the square of the diameter, of course, the gravitational constant, density, slip correction factor, viscosity, and so forth, right? And then you can play with these just for students to realize. If I have a 10 nanometer particle, right? You can see that the terminal settling velocity is really tiny. Of course, you have to have some feel for numbers, meters per second. The time to drop 100 meters is 48 years. Some of us have been around for 48 years. Many of the students here have not been around. So a particle that I released 48 years ago is still floating around for you to come and experience it. So this is profound, simple calculation, right? As the particle size goes up, the residence time goes down, right? So simple things, playing with numbers, very important. I can shoot this particle, I'm jumping from topic to topic, pardon me, in a certain velocity field, and there is a distance that the particle traverses before it stops. Of course, if you're painting from a spray can, you will be surprised. The spray can is designed to generate a droplet of a certain size that it's going to go and hit the surface. Of course, you want to be at a certain distance from the surface. So the pressure in the spray can, all of this is calculated based on a stopping distance. The Stokes number is a fundamental parameter that we use. And you can solve for this and things like that. I'll skip these equations. I use that simple concept in design of an impactor, right? We saw a lot of impactors talked about today. And depending on the initial velocity, which is this expression in the Stokes number, you of course control it by the nozzle size, but depending on the particle size, you're going to trap or capture particles of a certain Stokes number, and the other stuff will keep going down. I can have a cascade of stages, and again, simple concept of stopping distance being used to design a cascade impactor. Okay, let me leave high velocity impactors aside. Impaction is the basis of PM 2.5 measurements mandated by the US EPA. You'll find a couple of these around in Miami region, all over the United States. I can have different cut sizes and get PM 10, PM 2.5. So of profound implication and used very extensively. So this is my simple concept of transport. I'm not talking of charged particle transport and other things. The last topic I want to, in the remaining time, is understand nucleation and condensation. I think tomorrow you're going to see some instruments operating on these principles. So nucleation is a fabulous thing. Where do particles come from? I showed you starting from molecules. So you're in some sense answering the holy grail question. Where do these things come from? Of course, I can kick up dust, and then those are particles already there. That's a different mechanism, but the very basic question, and I can refer to a classical theory, which most of the time doesn't work, at least in our aerosol reactors, but I'll still talk about it because it's good classroom material and good to get started to at least illustrate some of the concepts. And I'll talk about condensation. And I want to end with sort of combining some of this and talk about a very relevant example. So again, very quickly, the life cycle of ultrafine particles. there might be a primary source, there might be secondary conversion, all kinds of stuff, and then impacts on climate, health, and so forth. That's why it sort of justifies understanding this simple free energy estimation of a molecule particle system or vapor particle system. So if I look at the free energy change, final minus initial, final is particles, we call them embryos, and the remnant vapor, because not all vapor molecules will become particles. And of course, initially I start with pure vapor, a pure set of molecules, right? I can write this expression for the free energy. Of course, I now bring in all the notation, the specific free energy, the surface energy, which gives me the difference between a particle state and the vapor state, do some simple manipulations, and then some more. You know, we are going through this very rapidly, but I plot this free energy change as a function of cluster size. If the saturation ratio, and the expression looks something like this, there are two terms, A and B. If the saturation ratio is less than 1, this is a negative term, so this becomes positive. So the free energy keeps on increasing. I never reach a stable state. Very interestingly, if the saturation ratio is greater than 1, I have a sort of peak, what we refer to as a metastable state. So nucleation is a metastable process. And if I cross this side, then it's going to sort of sustain itself, or the particles will grow. So this is the critical size, or the smallest size that is feasible in a system. Again, if it is not saturated, I'm not even going to cluster and form particles, remain in the molecular state. But if it exceeds that, there is a sort of minimum size, and the expression is given by a simple relationship like this, that I can calculate these things. I can look at this in another way by looking at the number of clusters. When S is greater than 1, it goes through a minimum. When S is less than 1, as I go smaller, this just increases, but as I go larger, the number just drops off. Just another way of looking at it. So simple thermodynamic estimations allow us to do calculations like this. So if S is 1, the minimum size is infinitely large, so I'll never nucleate. Anything greater than 1, at least theoretically, as per the classical theory, I begin to form clusters, and you can see the cluster size as F exceeds. So if I have a more saturated system, I need the fewer molecules to come together to form a stable cluster. Okay, so again, simple nucleation theories, the rate, it's not only that critical size, I want to know at what rate am I forming these. This is of course a longish expression. Let's just take it as a given, depends on the concentrations, the critical cluster size, the surface energies, of course, the saturation ratio, and so forth. And I can look at these. I'm not going to go through this. Let's look at the other aspect, which is condensation, right? And of course, there's a reverse to condensation, which is evaporation. We are going to see instruments which rely on condensation. You also heard about it. But there's a lot of evaporative systems. Some of you students drink instant coffee. I know Aranza was complaining about the coffee, but if you want decaffeinated coffee, you'll be surprised it's made by a spray process. They strip the caffeine out by using organic solvents. So decaf is not good because you have remnant organic solvents, don't drink it. And it also doesn't give you the kick. So I don't know why you drink it. But it's done by an aerosol process, right? And these are humongous systems. And spray drying is a process used very extensively. Threat of COVID is another very important thing, and I'll talk about it. Let me skip these equations for condensation, but just say that the growth in particle size is inversely proportional to the particle diameter. So a small particle increases in size at a much more rapid rate compared to a larger particle. Okay, so they catch up. So that's why condensation tends to make particles more uniform and make it more monodispersed. And in an engineered system, I might want to rely on condensational growth mechanisms to generate monodispersed aerosols. Let me skip the CPC. I think you're going to hear about it tomorrow. You're going to see it at this session because I'm running out of time too. Let me put everything together and it starts looking like a complex equation. We call it the general dynamic equation. The change of the size distribution function with time, that's what I'm after, might change due to transport, right? Might change due to Brownian motion. Things might move out and they might interact with each other. I didn't even talk about volitional growth. They might grow by condensation. New stuff might come into existence by nucleation. If I put these all together and we develop these codes, so students who are here who want access to codes, and you can see it'll be pages long because we need to then solve this, right? So all these different mechanisms come together in really explaining or describing a certain specific system. Let me apply to something very pertinent, right? And then those who are wearing masks will thank me. Those who are not should start wearing masks, and including myself. I actually have one in my pocket. I never wear it for some reason, but let's see this, right? We know about size distributions. I know about an individual, myself talking here, giving out this aerosol, right? You can't see it, small droplets, okay? I might be sneezing, I might be coughing, I might be singing. There is a certain emission of droplets, right? I might just be sitting here breathing in and out, might be giving out a low concentration. If I happen to be infected, of course, you're going to run away from me far, right? But we need to understand this. So let's say this is the size distribution of emissions. There are folks who actually quantify, use one of the TSI instruments, measure these out, or use other instruments. And let's say this is a typical size distribution. If I wear a mask, I'm going to reduce the number concentration for sure. And this is qualitative. The large particles would be removed more effectively. And I have that red distribution. Okay, that's me, the source of particles. Now let's see what y'all are doing here. These particles are moving towards you. So the last backbencher, you're somewhat safe, but maybe not as much. These droplets, I have a certain humidity in my system. I give out a droplet. Remember the condensation or the evaporation process? The droplet is going to evaporate because typically the ambient humidity, especially in the winter time, Florida, of course, the humidity goes up, but I'm going to have a loss of volatile material, in this case, water, and it's going to shrink in size. The large droplets are just going to settle out. Remember that settling velocity expression and so forth that I talked about. But then the distribution changes, again, the initial distribution, and you see that the distribution a certain distance away has reduced in concentration. And I have different cases, right? If I were wearing a mask, if someone else is wearing a mask, maybe the exposure is even lower and so forth. So let me bring in the receptor who's constantly inhaling your breathing. That's the beauty of aerosols. You know, the drinking water folks, they say, oh, the water is contaminated. You can get a water bottle and consume that. Air, you don't have that choice. Whatever air we provide, you're breathing unless you're bringing your own oxygen tank with you, which rarely is done. So very interestingly, the inhalation process is another aerosol process and tells me what is going to be deposited. But let me track this droplet. So this is single droplet transport. I'm just looking at two phenomena, combining settling with evaporation. This is the evaporation equation, or you might say the reverse of the condensation equation. It depends on the ambient humidity minus the surface humidity on the droplet, or the surface vapor pressure on the droplet, you know, the Newton correction factor and so forth. I have, of course, a relationship for what is the surface vapor pressure. It depends on what is in the droplet. Typically, it might be a salt containing droplet, right? So I have to account for a solute effect, the Kelvin effect, and then let's look at this evaporation time. So this is a simple solution of this equation. Depending on the initial diameter, it tells me how much time I'll take for the diameter to drop to zero. Obviously, I have to choose an ambient condition. And let's say this is, I think it's 30% ambient humidity, which is a typical number for an, let's say, indoor environment. So as the droplet becomes larger, the time to completely disappear, evaporate, becomes larger too. By the way, it doesn't completely disappear because there might be stuff in the droplet. There might be salts dissolved, and there is a certain equilibrium that is reached. So I shouldn't say completely disappear, but reach its final size. The same way I can calculate the settling time, and that's the red dotted curve, right? Knowing the diameter of the droplet, it takes a certain time to drop a certain distance. Of course, I choose maybe 6 meters and so forth, or 10 meters. It's the time to drop. And as the particle becomes larger, the settling time reduces. Okay, but this droplet is evaporating. Something very interesting to observe, something very simple, right? So for large droplets, it doesn't matter what evaporation is doing. The particle settles out, it's completely dominated by that. If the particle size is smaller, there's a shift in this curve because the size decreases and the settling time actually increases. And then there's a transition regime. So all I can do is, instead of the initial particle size, I can use an effective size and do this calculation. And my goal is to see, is there a risk from particles that we are emitting, and if they contain viruses, what might be the situation. So simple things like this. I can use this then to calculate the distance traversed in this horizontal direction. And this is just a graph. Depending on if I were coughing or sneezing, I have a distribution and a certain mean size, right? And depending on the droplet size emitted, the horizontal distance traversed, you might use something like this. We heard a lot about 6 feet separation. You heard that all the time. You go everywhere, you see those spacings marked in the stores. Maybe 6 feet is not enough, depending on the conditions. You were speaking, when you're coughing, sneezing. So one can do simple calculations to get a good idea for this. And then, of course, the respiratory deposition, because ultimately that's of importance to me. Very interesting size-dependent deposition, right? You might already know this, but different regions of the respiratory tract as a function of size. So this has multitude of applications. If I want to deliver particles of a certain size into the alveoli, I might intentionally use this size. If I want to understand a virus, where does it end up? I will use something like this. So I do the same for that emitted distribution. And of course, then once you inhale it, it deposits. You can then also calculate a risk for infection. And I just end, this is my last slide. You can make a nice graph like this. If I have a low efficiency cloth mask, it definitely helps some, but you can see it doesn't help too much. Whereas if I have a surgical mask or maybe even an N95 mask, it's just chopping the particles that get into my system, and one can then calculate a risk from all these different procedures, right? All of this is summarized in this paper. Have fun looking at the detailed equations. While I present it in a very simple manner, there's some numerical integration that is done. So obviously, it's very obvious that the minimum risk is if both the emitter and the inhaler are wearing these masks, and that shows up on the right-hand side of these curves, okay? So again, nucleation, condensation, evaporation, these are all important. Ultimately, we put it together in a general dynamic equation and look at this. So overall summary in the 40 minutes, little more maybe, and you can see where particles come from, what it is, how does it move around, how is it firstly characterized, how does it come into existence, how does it grow, and then of course, depending on the situation, you want to write code to combine all of this. So hopefully for the students, this is good. We do have classes here, so those who are from Miami, take it. In fact, my chair is here, right? He didn't make me teach it, but I'll give him the credit. He's forcing his dean to teach a class. So I'm going to teach the class for the 36th year now, after a year's break. So for the students, please enjoy. Thank you for listening. I hope everyone didn't fall asleep. Senior folks, wake up. I want to make an announcement now, changing topics. We do have dinner. So tomorrow, some of you took the tour and you saw empty labs. We are still moving in, but on the other campus where Cassie, Paquita, and some of the others work, my lab is also temporarily located there. Because we finish at 4 o'clock, if you're interested in driving over with our students to see the lab, that's a populated lab with several instruments, several research projects underway. Please sign. Shalini, you want to raise your hand? Please take your name. We can arrange for a carpool and then bring you back here. Okay, if you are hanging around in beautiful Miami, you might want to also see an aerosol lab. After that, there's a happy hour on the Erasmus campus. Is that correct?
Yes.
So you get, is it half price or free? Not free. Nothing is free. Half price? No, no, but there is.
It's there.
It's there. Okay. So after seeing the lab, after 2 days of so much aerosol science, you might want to grab a beer or a drink. So we do have that. By the way, the Erasmus campus is beautiful. It's next to, the students don't want to move out. I think they have a beach and all of that there.
Yeah.
So these students want to just hang out there. So it'll be worth a visit if you're around in town, right? With that, I'll hand over. We do have the demo session now, right? Yes, please.
Yes, I just want to add, tomorrow, the happy hour, restaurant called Happy Hour is invited, so Splendid is fantastic, so we will welcome you there. And right now, we want to go to the instrument session. We will first have, Dr. Liu Chen to introduce, from Physics Scientific Institute. To give there will be 3 companies to give, presentations. And then will be an instrument demo session.
Yes.
It's there already.
So when I move, I think that's.
Yes. Yes.
That works too.
This one will work too. I will put it in.
Thank you, Jerry. I first like to thank Professor Wu inviting me to this wonderful workshop. It's a very nice retreat for me and escape for a few days from the freezing weather in Colorado. We are actually, there's a storm warning in Colorado right now. We're going to get many inches of snow this evening, tonight. But anyhow, this is an honor to give a brief introduction of my company and our products. We are a research and development company located in Colorado. So this company is actually 2 companies. So Panic Scientific was founded in 2015, so a little over 7 years ago in Boulder, and where I have lived for 26 or 28 years. And also the Aerosol devices were founded in 2014 by Pat Keeley and Dr. Susan Harry. So the two companies merged about 6 months ago because Pat Keeley wants to retire, and so there's a very convenient, there's a lot of synergies between the two small companies, so we just decided to merge together. And now there were still two companies legal, and but Aerosol Devices act as operate as a division of Henderson. So we have been developing scientific instruments, mostly aerosol instruments, with personal investment and also SBIR, STTR grants. We also have been doing basic scientific research, with the government grants. So these are the funding agencies for us over the past 7-8 years. And so we have received quite a few SBIR projects and also science projects from DOE, from NASA, NSF, Navy, etc. And we have a few products as a company, and so we have, well, I can group them roughly into two groups. On the left is are the aerosol samplers from Aerosol Devices, and these are the water-based condensation-based growth tube caps instruments. And on the right, it's the Hynix Scientific instrument we originally developed, and one of them is called POPS. It's optical particle spectrometer, gives you size and number concentration. And we also have this called CFDC, which is ice nucleating, detect ice nucleating particles from the sample aerosol. And we also distribute the instrument. It's the Magic CPC made by Aerosol Dynamics. So those we have a few smaller accessories and a few late-stage instruments like a miniaturized CCN counter. And so you can think of Hynix Scientific was mostly focused on the climate effects of aerosols. And so the Aerosol Devices instruments were mostly on the health effects. Roughly, you can think that way. So this is just one chart showing the efficiency, collection efficiency of Aerosol Dynamics samplers, collectors, in comparing to other more traditional samplers. We have much higher efficiency, collection efficiency, and especially in the smaller particles size range, below, let's say, 500 nanometers. And it's uniformly effective, and the efficiency is about very close to 100%. So more than 90% uniformly from about 5 nanometers to all the way to 10 microns. So, and we have several models. One is the BioSpot Vivus, and this instrument over there in the back, and Jim, it's the smaller one. It's called BioSpot Jim, and also there's a spot sample. But all three models, and there's other models, they share the same technology, the growth tube capture, and with very high efficiencies. And so this class of instrument, they collect samples and to be analyzed subsequently by other analytical tools, which we don't have, and which I really want to develop something so that we can have an integrated instrument rather than two separate things. But with other analytical tools, you can do a lot of things with the sample. And there was many applications for the samplers. And I think the most famous one probably is that the paper by Florida group and University of Florida in Gainesville, Professor Wu et al. And there was this paper really demonstrated for the first time that COVID virus is transmitted in the air. Viral virus can be captured in the air in the patient. So this is the MAGIC CPC. It's a water-based condensation particle counter, and also measures the particle from about 5 nanometers all the way to 10 microns. And it's being used. This is a typical. It's very interesting. It's typical, and so it can be used in different scenarios, like very lightweight, and it can be used on UAV. And also, this is I think this is Katie just riding this this instrument on her bicycle. And this is the POPs. And the POPs, this is our first commercial product, and we have the company was formed to commercialize this product actually 7 years ago, and it's a very lightweight and instrument. It's about the core instrument is about 600 grams, and so it's being widely used in drone applications. So whether you use a weather balloon and can carry this instrument from the ground to the stratosphere, and that's the most widely used applications. And this instrument also, because it's relatively cheap, it's roughly a little over 10K, much cheaper. It's about maybe 1/5 of the of those big optical counters, and but with a very similar quality, scientific quality. So we have sold quite a few of those. It's about 350 in the past few years. It's quite popular product in this small field, and yeah, you can use it on the UAV, on weather balloon, on tether balloon, and also in the past few years we have deployed 2 networked brands, networked aerosol monitoring sites. So one is deployed by NOAA and DOE in Oklahoma. So there's about, I think, 20 some units deployed there. And also our company, we have a DOE supported project in Crestview in the mountains of Colorado. We have deployed 6 stations. In each station, there's a POP instrument, and there's a miniature CCN counter, and there's a time-resolved aerosol sampler who can collect samples and do offline measurements. So this is the I believe it's a direction, because for the future, and because we have very expensive aerosol instruments, but they can only deploy in certain points, very few data. But if you're and there's no vertical data, almost no vertical data. With this one, we can collect the vertical profiles. I think that's the biggest contribution. And also, because it's relatively cheap, you can deploy many of those instruments in a network, so you can get higher spatial resolution. And I think that's it for a very brief introduction of our company and our products. So I'd like to thank you for your attention. And for more information, if you want to know more, and just visit our website, panicscientific.com, aerosoldevices.com, and also reach out to me through emails. Thank you very much.
Thank you, Lee. So next, let's welcome Varun to present for Silver Cooper. Thank you.
If you could press F11, it'll switch to slideshow.
Thank you.
Thanks. Well, I'm Varun Yadav from Silver Cooper, which is the parent company of Cooper Environmental. And before I begin, I want to thank Professor Biswas for that masterclass in aerosol science. It's no matter how many times we have gone through it, it's still amazing to hear from the expert. I want to very quickly, this was not an easy presentation to make. It's not very long, it's very short. I was trying to think of how to best structure it, given that we have such expertise here already. So and the other thing is, other challenges, we either work with industrial clients who do not want their data out, or we work with researchers who wish to publish their data. So at best, I can provide you as references. So I'll provide a very general introduction to our products. However, what I want to focus on is the applications that they have and some of the fun new applications that we've been trying with some of our research in the research community. So Cooper Environmental was founded by Dr. John Cooper in 1996, and the main focus was that we would be measuring metals by using X-ray fluorescence technology. So at this point, the company has about 20 years of experience, and over the years, we have expanded to have a global footprint. Majority of our clients are in China, US, Europe, but we have also expanded into other countries, Southeast Asia, we're working through there, and including Middle East and South America. So if there's a project in Antarctica, please let me know, because that's one continent that's still left. We'll be glad to get there. A couple of years back, we were purchased by a Chinese company called Hebei Hero. They're one of the largest private manufacturers of air quality monitoring equipment in China. And since then, it was helpful to get that investment to be able to expand out globally. And over the years, they also purchased another company called Sunset ECOC. So we are like sister companies. We maintain our own independent operations. We do metals monitoring, they do carbon monitoring, and we get along pretty well. So the key instruments that we have are Exact 625i, which is probably the one that is most people have heard about. It's the unit for measuring metals in real time for ambient monitoring. But we also have a couple of other instruments that we have developed. The 920 is for continuous monitoring of metals in the water medium. And 640i is the one for doing measurements in stack. We also, when we created these instruments, one of the problems we ran into, how do you quantify what you're getting when there's no known standards out there? So we ended up creating aerosol, quantitative aerosol generator in-house so that we could do factory acceptance on these equipment and make sure that they are producing what we claim to be producing. So over the years, we have 9 patents on these technologies, and we have done a lot of collaborative work with US EPA, Eli Lilly, as well as EPRI over the past years. And given John's background, John Cooper, he was involved with developing the speciate database of source profiles. We also do source apportionment and chemical mass balance consultancy work, as well as providing analytical services and working with industries to help develop proposals for monitoring. So 625i is the most well-known equipment, but I'm going to start with the one that started it all, the 640. This was the world's first commercially available stack metals emission monitoring equipment. At this point, it has the ability to measure up to 65 different elements, bring especially arsenic, cadmium, chromium, which are of interest to the coal power industry as well as incinerators. It's the only metals sensor monitor that has been approved by US EPA and validated by method 301. And in 2007, it was recognized by US EPA with the Clean Air Excellence Award for outstanding achievement in clean air technology. So very quickly, it's used in it has been used in lead smelters and coal power plants and waste incinerators to not only measure what's coming out, but also to help optimize the process that the industry is using so they could reduce some other pollution. And here's at the bottom there's some graphs that showing how well it correlates with the reference that for these measurements. The other equipment that we developed is the 920, where we sample metals by taking a stream of water and then aerosolizing that water and then collecting it on a filter and then measuring metals continuously in real time. It can simultaneously measure up to 65 different elements and compares pretty well with ICP-MS in the lab as well. So some of the applications, again, it can be used for industrial process control and optimization, as well as we've seen applications with coal-fired plants in trying to do the ash point remediation. And one of the fun new application that has come out is that in California, we were working with certain researchers and we realized that strontium could be a very good surrogate for bioalgae blooms. So we have optimized equipment so that we can do really good measurements of strontium, even at low level, so that it can be used for water remediation purpose. And it could have application in potentially areas where water is a very scarce resource, so that water recycling can be improved, the process can be improved. So completely unexpected, but that's another way that we are trying to utilize the equipment. Finally, the Exact 625i, the one that everyone knows about, thanks to the Axon network as well recently. So this is where I'll go into a little more detail about the way the instrument functions. The way you can think about it, the previous two equipment all rely on the same technology. This is the heart of our equipment, and then the other things are basically different accessories that we put on top of it for different applications. So this particular instrument is used for doing ambient monitoring of metals. At any given time, we can measure up to 67 different metals, though we tend to, most researchers tend to focus on a smaller group for different reasons. As of now, we have over 300 installations globally, and it has been validated by US EPA for the ETP program and referenced numerous in research papers globally. The elements shown on the periodic table in blue are the ones that can be measured by the equipment, though some of the lanthanide and the radioactive elements, we don't really give detection limits for them because we don't have standards for them. So we don't know how to best characterize it, but by the characteristics of X-ray fluorescence itself, we know that it measures it. It's just that the detection limit itself, we don't know what would be the ideal one. The most common configuration used is 44 metals, which includes the analyzer the researchers are interested in, as well as the interfering elements combined together to do the measurements. The advantage of X-ray fluorescence is that you can go down to very low scale, even picogram scale, if you're going to do that measurements. And in comparison with ICP-MS, it tends to do pretty well. ICP-MS and XRFP also tend to have an argument as to who is the one that's biased, who is the reference. So I like to claim that we don't have operator errors, at least in the XR side, so maybe we are better, but I'm sure ICP will have a different viewpoint on that. So the main reason why these equipments are used is, of course, for characterizing pollution, the chemical composition, as Professor Biswas was mentioning earlier. Globally, it's used for PM 2.5, PM10 air pollution characterizing them, and then the trace with the metals. The main reason is even though metals are basically less than 10% of the total PM fraction, they tend to be the key tracers that can be used to correlate to the sources being observed. So EXACT has been used in combination with many other different equipments performing measurements in real time, like the Methven BAM or even Aerodyne's ACMS, the Sunset one, or even the McGee Scientific's carbon measurement equipment. In some of the more recent applications, we have also tried to see if we can use it for industrial hygiene for OSHA requirements, and we are evaluating how that could work out. Quite expensive for that application, though. So the main advantage of this instrument is that we can do sampling in different time modes. Compared to the traditional way of doing PM10 and PM2.5 measurement, where you do a 24-hour integrated filter and now capture the particulate on a 24-hour integrated sampling, then bring it into the lab and analyze. With this equipment, right in real time, you can perform analysis in either 15 minutes more, 15 minutes, 30 minutes, an hour, 2 hours, 3 hours, 4 hours. The 1 hour is the most commonly used one by researchers, and it provides a good understanding of the source characteristics happening on a smaller time scale. We have been working with one of the, well, I think I can say it. Yeah, they recently published it. South Coast Air Quality Management District. They wanted us to develop ultra fine time resolution mode. So we developed a 5-minute option, and we were surprised to see. Initially, we thought that we would not be able to measure much at all because the metals are such a small fraction. But when what they did was they took the instrument into a mobile in a mobile setting and drove it around the industrial area. And when the plumes hit it, even in 5-minute mode, we were able to see very clear peaks of high metal concentration. So the key advantage is that it has onboard meteorological sensor as well. So wind speed, wind direction is being captured, as well as it has a real-time data analysis capability as well. So when we combine all that, and when we are looking at smaller timescale resolutions, we are able to pick out sources very easily. And that's the key advantage of having the high time resolution with such large amount of data being collected at the same time. Now, I'd like to end it very quickly here with the number of users that have been installed. It's a short list of some of our collaborators, both in the academia side as well as on the environmental regulatory agency side. The couple of things I want to bring up in terms of the applications. We collaborate with quite a few different researchers, and some of the applications are interesting. They may or may not work. One particular research group in Europe, they decided that they wanted to see how the instrument could be characterized for optimizing a nanoparticle generation process. So we helped them hack the instrument, our own instrument, to run in 1-minute mode. And they would do their process with palladium and silver, and we would try to measure it and give them instantaneous results so they knew how to optimize the process that they were trying to aim for. Of course, by the time they ended, they pretty much destroyed the sampling system. So it was, but still a fun experiment. Recently, as everyone knows here, quite a lot of people we've already talked about this. EXACT was included into the ASCENT network, and that will be the first real-time network being established across US, funded by National Science Foundation. And we are very, very honored that we are part of that. The other thing I want to bring up, given the number of researchers we have across Europe over the years, we decided that it would be good to bring them together, and we formed a XRF user group in Europe. And we've been working together to try to see if we can come up with a study to do a continental scale wide real-time metals monitoring data and examination to see long-term regional contribution of metals, how it's changing, and the variability and how it's impacting health out there. Maybe in future with the group that we have here, Ascend Network, it's possible that we could do that in US as well. And my ultimate dream, try to combine the two continents together and see what we come up with. So with that, I would like to leave my contact here, and if there's any questions, please feel free to catch me anytime.
Okay, let's welcome our last presentation today, delivered by Dr. Steve Brett from TSI. Yes, if you want.
Is this? I'll just use the keyboard. Hi, I'm Tim Wright. I'm the Southeast Regional Manager for TSI. So many of you are my customers, or hope to be my customers. I want to thank Young and Pradeep for putting this on. This has been a great workshop. I look forward to seeing it next year, see how things grow. And I especially want to thank you for taking me down memory lane for 8 years in 40 minutes. That was, I was like, oh yeah, I remember that. I want to start out with talking about this this measurement that we did at TSI. This is one of our instruments I'll showcase you in a second, but it was we were just monitoring. We put up sometimes our instruments on our buildings to see what's going on, just to make sure they work, make sure we understand what we're seeing. We got a fairly boring size distribution here of from an SNPS, peaks at 100 nanometers. Then 15 minutes later was a spike. And we suspect like a semi drove by or something. So we got this nice big peak. But the one thing I'm going to draw your attention to here is the number concentration, the total number concentration climbed 5-fold. But if you looked at the mass, this is a derived mass, it's not an actual like a direct mass measurement, it stayed the same. And this has come up a lot recently with ambient monitoring. PM 2.5 is almost invisible. These sub 100 nanometer particles are very invisible in the PM mass-based measurements, which is why we've been encouraged to look into SNPS monitoring. So we've brought in a new instrument into our SNPS lineup. So this is now our 4th DMA. So called the wide range DMA. It's a kind of a squat thing, and the particles don't come in at the top, they come in at the bottom. It's kind of an odd configuration. It's actually been used in Europe through the Tropos network. And through a lot of collaboration, we have created a whole new system here. And so this is kind of the complete big version of it. So you have the sampling mass at the top with that goes into and splits into the particle counter to get total particle concentration at the bottom. And then there's the SNPS on the right-hand side with the new DMA and CPC. We've been using, Europe prefers to use the butanol CPC, the 3750. But Ascend recently incorporated this new SNPS into the 12 stations across the US. And due to requirements of various sites has chosen to use the water CPC. So hopefully in the next month or two, these will be actually in the field. We're really excited to have that going out there. And just for completeness, we do have some accessories that can go along with a new monitoring station if that's something that's interesting for you. As I said, Ascend is the 12th site, but it's also TSI also participates in a lot of other sites. Actress is kind of a broad world network. With these, 22 countries, 79 sites. We have not just SMPSs, the DAPS, various other instruments that I'll cover briefly, try to keep it short too. And so just kind of wanted to bring this home that TSI isn't just about the SMPS. It's kind of our big thing in research and analytics, the division I am in. But TSI also has its fingers in so many other industries and so many other aspects of research. From particle counting, sizing, we have the different types of sizers, supermicron, submicron, we do aerosol generation, filter testing, and filtration technology. And then outside of research, we have indoor air quality. There's the clean room detection, particles in clean rooms. So basically, if you're dealing with aerosol and want to talk about it in any sort of thing, give me a call and see what we can turn up in our portfolio. So we brought a suite of instruments with us, and I'm just going to give you a brief rundown. I think many of you probably are experienced with these, and we can do some hands-on tinkering with these to show you guys more up close. But first is going to be OPS. This is an instrument that's just it's small, you can see it back there, but it's it was really designed for deploying it out in the field. We sell enclosures for it to, environmental enclosures. It has battery life onboard storage, about 8 hours of operation. 300 nanometers at 10 microns and 16 channels. It's pretty bread and butter, but it's an OPS. So. And then there's the APS, which while covering roughly the same size range, it goes up to 20 microns and it's higher resolution. This has seen a lot of use recently and deployed in Europe alongside our SMPS to get the full size range from 10 nanometers all the way up to 20 microns. So it uses time of flight to define the particle size. So it's a different technology. Composition doesn't matter. So it's doesn't have to worry about X-ray refraction. It's just, hey, this is your particle size. And finally not finally, this is our line. We have a line of impactors. The very common Anderson impactor. These are called Moody's. So there's a shift. They have a higher cut point. So it's deeper, less transition between the stages. A standard Moody has just measured straight onto a straight plate. We have rotating Moody's where the stage rotates so that the particles don't build up and bounce off as much. And finally, one that's kind of many people don't realize is we have what's called the quartz crystal microbalance, which is QCM Moody. And so it's 6 stages, but this gives you real-time mass measurement. So it tracks each stage gives you a 1 hertz data on how much mass is built on each stage. And then there's our suite of SMPSs. So these are just 3 of them. General application SMPS, the long DMA is kind of the classic everybody's familiar with. Does 10 to 650 nanometers in a single scan. It can be adjusted to shift up to that 1000 nanometers. Our new ultrafine measurement system, which the wide range DMA does 10 to 800 nanometers in a single scan through both a combination of the change in the kind of the physics of the column, but also in some new scanning techniques that we have. And then finally, we have sub-10 nanometer systems. What we have back here is actually the nano DMA with the water CPC that can go down to 2.2 nanometers. Changing things out, we can put a DEG on front of a butanol CPC and get down to 1.2 nanometers. So just a quick summary of what we do. Like I said, we're everywhere it seems. We have our particle sizing from 10 nanometers up to 20 microns, sub 10 nanometers, but butanol and water-based CPCs. I didn't discuss it all, but we have a line of fast sizers. These are the FMPS and the EAPS. These are often used in combustion measurements or mobile measurements that need to do fast time resolution measurements. This 1 hertz or 10 hertz data collection. Particle generation, I didn't even touch on that, but we've got quite a suite of instruments from sub and super micron generation, mono, polydisperse, and liquid and dry. There's a whole line of filter testers and filtration efficiencies. And then outside of kind of the research and analytics field, we have dust track monitoring for colorimetric, which can be used not in place of EPA PM measurements, but can be used to enhance those. So that's about it. I just, the food's here and I guess you guys are probably getting hungry too.
So TSI has a demo set in the back of the room, so if you're interested in, feel free to stop by yourself. Yeah, and
Okay, good. Yeah, there'll be some demos. We have dinner also served. I wanted to take this opportunity to thank these three companies, TSI, Andix, and Say Cooper, for sponsoring this workshop. So let's give them a big hand. And we are meeting continue tomorrow. What time? 9, 8?
starting from 8 with the breakfast.
Yeah, 8 there'll be breakfast and 9 o'clock we'll start the session. So please enjoy. Thank you. Yes, sir.
Yeah.
Yeah.
The ticket for tomorrow.
Oh, okay. Yeah, I'll get something from.
Oh, no, I just was.
I think I'm just saying.
Okay, I'll get it from.
Yeah, but.
Yeah.
Yeah, I'm sorry.
So thank you for coming.
Yeah, well, I wanted to come yesterday, but, During that venture, what do you like to do? Yeah, that's right.
If you are around tomorrow. I'm leaving. I have to get tomorrow. Yeah.
Next time. Next time, yeah. Then now that you know, so this one. I'm not saying everyone, but he did, then, people either inject it back.
So,
Okay, okay. Where did you come from?